Okay, it's probably we've just gone past. I'm sure there'll be some more people who'll filter in over time, but I think we might as well just get the meeting started so we can stick reasonably to time. Also please, other panelists as well, let me know if there's any problem with my audio or anything. That would be good to know. But otherwise, welcome everyone. It's a real pleasure to have everyone here today. This is the Royal Astronomical Society specialist discussion meeting on planetary ultra-low frequency waves theory, modelling and observations. And so thanks, first of all, to everyone who submitted an abstract to make this meeting possible. And hopefully you'll agree we've got a really nice lineup of talks, all of which focusing on ULF waves. How often does that happen that we get such a specialised meeting as this, which is great. So as probably you've clicked an option to say this is okay, but the meeting is going to be recorded. So if you do have to run away for any time, I can't believe you would, because you'll be so addicted to the ULF wave discussion, which will be going on. But if you do, then the meeting will be recorded and that will be uploaded to the RAS YouTube channel probably just after the weekend, depending on when I get to it. So you can see all the talks and discussion at a later date. I've put the website link in the chat, so if you want access to the program, if you follow the link to the website, scroll down to the bottom, you'll find the program. We're going to be using, if you want to ask a question, please use the Q&A at the bottom, and that will come straight to us as the panelists, and then we can ask those questions back at the end of talks. You can also, I mean, I'm sure people will end up using the chat for various things, and that's also fine, and you can select who that goes to, and we'll keep an eye on that as well. But generally, Q&A would be better for direct questions, would be good. For speakers, roughly 12-minute talks. We've got 15-minute slots for everyone, so roughly 12-minute talks would be great, with a couple of minutes for questions and then a minute for switching the screens over to someone else. So if you could please try and stick to that, that would be fantastic. Otherwise, your chair for the first session is going to be Matt James, and I'm sure he'll be keeping you to task. There's another thing, yeah, I mean, we already mentioned that we're in the Zoom webinar format. So if you are a speaker, you'll be promoted to the stage, if you will, or to the panel before your talk. And one thing that wasn't mentioned when we advertised, because I didn't know this was going to be the case, as the construction noise outside my house gets louder and louder. So apologies for that. But basically, we've got the Zoom room open at the end of the session, at the end of the day as well. So from 3:30 or roughly when we finish, if anyone wants to stick around and have a kind of casual cup of tea discussion as you would at the usual end of an RAS meeting or at a conference, then please feel free to stick around. We'll be able to promote everyone so that everyone to the panel so that everyone can see everyone else. And if you want to ask speakers if they're still there, any questions, feel free to do that then. That also is probably a bit more, a bit better for our American friends as well. I'm very impressed that some of them are here. That's commitment to the cause. So yeah, so basically we've got some discussion time at the end, but it's very, if no one stays, no one stays. It's not a problem. It's just we have the Zoom room open, so everyone can just stay on the same link and we can all just have a chat if you like. But with that, that's more than enough from me. So Matt James is going to be chairing this first session. So I am going to hand over to Matt to introduce our first speaker. Thank you very much, Matt.
Thank you, Tom. Welcome everyone to the very first session. So I'd like to welcome our first speaker, our invited speaker, Martin Archer. If you're capable of sharing your screen again, that would be brilliant. So Martin is going to be talking to us about surface, fast magnetosonic and alpha waves in high resolution global MHD simulations. I'll probably give you a warning when your slot is about 5 minutes from the end, if that's all right.
Yep.
And yeah, brilliant. So please take it away when you're ready, Martin.
Okay, thank you. Yeah, so to anyone who doesn't know me, my name is Martin Archer. I'm a UKRI Stephen Hawking Fellow at Imperial College London. I'd like to thank the organisers for the invitation to talk at this meeting. And I'd also like to thank all my collaborators who've greatly contributed to the work I'm going to summarise in this talk. Now, given that I'm first up, I thought it's worthwhile to introduce ultra-low frequency waves with a diagram that hopefully some of you may have seen before. So in our field, ULF, usually refers to anything less than 1 hertz in frequency. And often what we mean by ULF waves are actually magnetohydrodynamic waves within our magnetosphere. Now, these can often be set up as resonances or standing waves within the different boundaries present. And I like to think of our magnetosphere as like a giant magnetic musical instrument with all of these different wave modes that can be excited. People should be familiar with the Alfvén mode, which propagates along field lines due to magnetic tension. And so often we can see these as, say, like a field line resonance, almost akin to a guitar string being plucked, like a field line that gets plucked by, say, like a solar wind impulse. Across the field, though, however, we have the fast magnetosonic mode, and often that can bounce radially between boundaries such as the magnetopores or the plasma pores, which is the edge of the cold torus of plasma, or even turning points. And when we refer to cavity or waveguide modes, that's usually what we refer to what's going on, waves that are sort of bouncing radially but may also be propagating in the azimuthal direction. And then finally, one that is not often so much introduced to introduction to MHD waves, other than the body waves, are the surface modes. So we have boundaries such as the magnetopores, which constitutes the outer edge of the magnetosphere, and you can have surface modes as well. So these form often due to either solar wind pressure perturbations or the velocity shear down the flanks that is present across the boundary, leading to surface waves. And in the limit that actually the finite extent of those field lines, in a similar way to the Alfvén mode, actually plays an important role, we can have these things called surface eigenmodes, which were first kind of proposed some 48 years ago. Anyway, so you can see there's lots of different wave modes present, and these can all be externally or even internally generated through a variety of different processes. So there's a real zoo of ULF wave phenomena can occur within our space environment. I'm going to be focusing on externally driven waves by the solar wind. And there's a sort of rule of thumb with those, or a paradigm, that because the solar wind obviously kind of travels tailwards, that any disturbances caused by the solar wind in the ULF band also tend to propagate in that same direction. That is the paradigm that has been fairly well established through decades of observations. Okay, I'm going to simplify things a little bit more now, because trying to do the full-blown theory is hard. So when ULF waves were first being sort of thought about, simplifications were made to the MHD equations to be able to understand these, using these so-called box models, where you treat the magnetospheric magnetic field as being a uniform field anchored by the ionospheres. And I'm showing examples of that here. And they've been really, really helpful in just picturing and understanding and even predicting some of the properties of the global dynamics of our magnetosphere. And what the box models really help you do is kind of tease out those different resonances that can be possible, the eigenmodes of the system. And so I'm just showing in these diagrams here what a surface, a cavity or waveguide, and an Alfvén mode look like within a box model, as well as some sort of predictions of how these perturbations associated with them should vary spatially and also in terms of their polarizations. And this is really where a lot of our predictions of what ULF waves should look like and how we diagnose them in observations has come from. But of course, this is a simplification, and we do need to understand where these models break down and where they're not representative of reality. And one of the ways that we can do this is through high resolution global magnetohydrodynamic simulations of the magnetosphere. So these are general purpose simulations, just solving the MHD equations. They're not ULF wave specific models, but they have some benefits over some of the other models that people may use. Firstly, you can get the inhomogeneous background plasma in a fairly realistic sense represented. More so, actually, the geometry of the magnetic field. You can see in these diagrams here, which show contours of footprints in latitude and in local time, that the magnetosphere is not really dipolar when you get to the outer magnetosphere. It differs substantially from that. And so that adds complications to try and do things analytically, but in an MHD simulation, we can reproduce that. Obviously, we also have a magnetosheath in these models, so we can self-consistently include that. And that's really important because it also means that we can reproduce the surface mode without having to try and impose it ourselves, which I think is the only way that you can really reproduce surface modes is through 3D global MHD simulations at the moment. So what I'm going to present here is a summary of some surprising results that have come out from a high-res run of the SWMF model, where we've excited ULF waves through a solar wind density pulse. And you can see the grid resolutions we're using here. So in the regions I'm going to be considering, which is this dashed line here, this dashed box, it goes from 1/16 near the inner boundary up to about 1/8 of an RE. So let me just show you quickly what is actually occurring in the simulation. So we hit the magnetosphere with a density pulse, you get a transient wash through the system, and then you can see here what I'm showing is the perturbations in the compressional component of the magnetic field. We're getting global scale waves being excited by this pressure pulse at the same frequency everywhere, basically. And what I'm going to dig through in this talk is some of the things we found out about this global mode that is being excited and comparing that to theory. So I'll start with actually the motion of the magnetopause itself. What I'm plotting on the right-hand side here is, as a function of time and then also local time, just the difference in the displacement from equilibrium of that magnetopause position. And we can characterize the motion in 3 phases, basically. We have the first phase where the pulse arrives and you get a strong compression of the magnetosphere. You then get a reversal of that. And what happens is the magnetopause rebounds, but it doesn't just go to the equilibrium position, it sort of overshoots a bit. And then in the third phase, which is the one I'm going to focus on, is we see these damped oscillations occurring. And actually, if you do a Fourier transform of those, what you can see is that there's a primary mode. The most intense mode is at about 1.8 millihertz, or about 10-minute period. And that's present at all local times, originating at the day side, but present basically everywhere. And really, that is the global mode that we were seeing in that video. However, there are smaller secondary modes at slightly higher frequencies, and frequencies vary with local time. And we can attribute those to the sort of innate Kelvin-Helmholtz type frequencies that you would expect to get if you didn't have another eigenmode present. So the other thing that we can see from this diagram here is actually that they're all growing in amplitude as you go down the tail. So the waves of both modes are basically increasing as you go down the tail. And that's interesting because not only do we have the innate Kelvin-Helmholtz where we basically expect that to happen, we're seeding fluctuations from the day side at our surface mode frequency, and that is also getting amplified by the Kelvin-Helmholtz instability. However, if we have a look at these 3 areas I've highlighted here, what's interesting is whilst in this region here and this region here, we can see that there's clearly inclined phase fronts and therefore tailward propagation. Across a wide local time range on the day side, their fronts are vertical, and it looks like there's no azimuthal propagation whatsoever. And that's surprising because we still do have magnetosheath flow, and it's not negligible in these sorts of regions. So how can you actually have this azimuthally stationary surface wave be possible when we know that the surface waves should get affected by the flow? So what we looked at was the Poynting flux and the different terms in Poynting's theorem to describe the energy flow that's going on. So I'll take you first to the panels on the right-hand side. What we're doing is a function of local time at the magnetopause, and also as a function of distance along the normal, so either into the magnetosheath or into the magnetosphere, looking at the time averaged fluxes. So what we have here is the Poynting flux, and we can see these big regions here that are indicating that actually the Poynting flux is pointed towards the subsolar point rather than down the tail. So that goes against that paradigm I was telling you about, where normally you would expect all the propagation to head tailward. If we then look at what's known as the advective flux, this is basically the magnetosheath advecting the wave perturbations tailward. That is as expected. We are getting that advective stuff. Now, what if we actually integrate along these normals and then look at the overall energy flow at each local time? You can see the opposition of the pointing flux and the advective flux, but actually across a wide local time range, if you add those two together, they cancel one another out. And that is basically how you can have this azimuthally stationary surface wave. It's a balance of energy flows that cancel one another out and allow wave energy to be trapped locally much longer than you would expect otherwise. But obviously past a point, then advection wins, and then you get the usual sort of tailward propagation. And we can understand this even within the box models, so in this diagram, as I've indicated. So this kind of is trying to explain the global surface wave motion of the magnetopause following a sort of solar eruption that can drive, say, space weather. Okay, I'll talk a little bit about waveguide modes now. So these are those modes that have fast magnetosonic modes propagating against the field. And the most clear indication that they might be present is kind of nodal structure. So nodes and antinodes in the compressional magnetic field across the background field. That is how they're most clear in say, simulations, and that's been shown in previous papers as well. And if we have a look at a near equatorial plane here, you can see there are various antinodes across the field and nodes like so. So there seem to be in the night side magnetosphere, waveguide modes being present. However, if you're a person who uses, say, spacecraft observations, it's often not possible for you to see kind of nodal structure across the field because you may only have a limited number of measurement points. So there have been common methods to try and identify these based on phase differences between the perpendicular component of the velocity, or equivalently electric field, and then also the compressions in the magnetic field. And usually it's the radial velocity that it is used. And that was first proposed by Waters et al. Based on some actually symmetric dipole models. However, what we've done here actually is instead relax that assumption and think about, well, what about if we consider all possible directions perpendicular to the field? And basically, if you look at the arrows, this is showing the direction in which those waves are actually standing. And you can see that it can be far from radial in the tail. And you can see the effects of refraction going on as well. So the standard method can actually fail in a realistic magnetosphere. And so we need to sort of relax the assumptions in our detection methods. And there's a similar sort of idea with detection methods for Alfvén modes, which have used the crossphase between a perpendicular component of the velocity and the same component of the magnetic field. If you look for quadrature between them, that's often used as a test for standing Alfvén waves. And we can see standing structure present throughout the magnetosphere. There's a field line resonance sort of here. There's a field line resonance here, which have been excited by that surface mode where the eigenfrequencies match. However, actually, realistically, what we're doing here is we're finding just standing structure along the field. It comes from the pointing flux. And so it's not only a test for Alfvén modes, because you can see it light up in regions where we know the frequencies of the Alfvén modes have to be a lot higher than this 1.8 megahertz global mode that we're exciting. So bear that in mind as well. Another common technique in diagnosing the waves is through polarization. So in, again, a near equatorial plane, what we can see is mostly throughout the magnetosphere, we have the polarizations that you'd expect in the velocity for tailward traveling disturbances. They get reversed on the day side. And that is, again, due to these waves propagating against the flow. So we're seeing that signature of the direction of propagation of the perturbations here. And that might be a way that we could use observations to try and sort of see this effect going on following events. However, of course, it's not often easy to measure the velocity or the electric field. So often we rely on the magnetic field and say that through the Alfvén-Sprosinin flux theorem, we expect to get basically the same sense of polarization. However, if I plot here the product of the two ellipticities, you can see these purple regions like so in the outer magnetosphere. The magnetic field has the opposite polarization to the velocity in our simulation. This is an effect of the magnetospheric cusp, actually, because if we look at the induction equation, hidden within this notation is basically, well, our background magnetic field is inhomogeneous. And along the field, it's getting depressions because of the cusps. And similarly, in this curl, we're basically hidden away our curvilinear geometric factors going on, which if you take them into account, then you will actually predict this opposite polarization.
There's about 4 or 5 minutes left now.
Great. Okay. And there's another surprising feature if we look in the noon meridian. So the radial and field aligned velocity perturbations show very nice fundamental standing structure along the field. But if you look at the compressions in the magnetic field, let's see if I can play that again. You have something that ends up looking more like third harmonic structure. And that again is a feature of the cusps coming into play here, which we've been able to show analytically as well in our papers. And the final thing I want to summarize quickly is just the magnetospheric current systems. So what I'm plotting here are the amplitudes of perpendicular and parallel currents, both in the near equatorial plane, but also as we get closer to the inner boundary. We can see that actually field-aligned currents are starting to light up near the inner boundary rather than perpendicular currents. And that's evidence here of the sort of coupling, non-resonant coupling between the compressional and the shear modes occurring in a realistic magnetosphere in a way that you don't get for a homogeneous box model. But what's interesting about this is the two lines I've plotted in the equatorial plane. The solid line is the open closed field line boundary, and the dashed line is the inner edge of the magnetopores. And you can see where they map to here. So actually, under northward IMF, we have an almost closed magnetosphere, but actually the field aligned currents seem to be occurring at the inner edge of the magnetopores. So rather than actually surface modes being evident at the ionosphere and at the ground at the open closed boundary, we might expect them to actually be further inward. And we're currently still doing ongoing work about predicting what the signatures in ionospheric and ground data of a surface mode realistically should look like. So this is my summary slide. The real take-home message is just remember the magnetosphere isn't a box or a symmetric dipole. We found a number of surprising events from this one run that we can actually explain from the full MHD equations as well. And if you want to know more, here are the two papers that have been published so far. Thank you very much.
Thank you, Martin. That was brilliant. Has anyone got any questions?
Yeah, so we've got a question in the chat from Li Jian Chen, and he says, fascinating talk, Martin. How large / strong is the density pulse? Do you envision fundamental differences if the density pulse is generated by the ion-ion instability in the foreshock? Yeah, so I mean, we've used quite a large density pulse in here. I think we go from about 4 or 5 per centimeter cubed up to something like about 14. That's largely because of just the numerical dissipation that you can get in global MHD codes. Depending on the model, there are some models that are less dissipative, so you might not need as big a pulse. I think what we've determined though actually is that really the effects that are going on here, we're not getting into the non-linear regime with half the things that we're showing. The thing that's important is the scale size of the perturbations, and that's really set by the length of the field lines. So it should be actually quite common to almost all sorts of drivers. If you're exciting large scale waves where the variations of the waves themselves are larger than the scales of inhomogeneities or the curvilinear kind of scale factors, then you start to get these bizarre effects. Cool. There's not another question, so do keep your questions coming in. Also, if Martin will probably be around at some point to answer any other questions later. Should you? I know it takes a while to type things out as well. With there not being another one, I will ask one if that's okay, Matt. So you talk about the surface mode coupling to a waveguide mode. I think in your papers you talk about the frequency difference. I mean, the surface mode being a lower frequency. And so there's a frequency matching. So how does this frequency matching occur, and kind of where does it occur? Yeah, so the surface mode is being excited on the day side, and on the day side region, you would expect that to be the lowest frequency mode. However, of course, as you go into the sort of night side and you have those surface modes that have Ks that are going down tail, obviously you're changing the eigenfrequencies as a function of local time, and so you can find regions where the waveguide mode is now actually
at the same frequency as the surface mode as it was on the day side. And since you're driving all the global dynamics from what's happening basically at noon, then that will basically dictate where you light up in waveguide modes and where you light up in Alphane modes. And that will be heavily dependent actually on the density configuration of the magnetosphere. So where we're seeing that light up in our MHD simulation versus where you might actually see that in reality or in statistics, they could be in completely different locations because our space environment is so incredibly variable.
Okay, cool. That makes sense. I'll just follow. I realize we're almost pushing the time of this one, but I'll just follow up with one quick follow up with one from Lee Jian Chen. It should be a very quick one, I think.
Yeah.
Could you say more about the scale, size, and 3D structure of the density pulse? Is the one you use the size of the entire magnetosphere?
Yeah, so it's planar and it's the size of the entire box here. So you basically hit the magnetoballs at all locations. But in one of our papers, we showed good agreement with, say, a localized magnetosheath jet, because a lot of the physics that's going on is local. And so it doesn't so it's kind of almost independent of the driver. You'll just you'll kind of bake in the scale size of the driver in the response, but actually a lot of the features that we're talking about along the field don't care about exactly how it was driven.
Thank you for answering those questions, Martin. So I'd like to move on to our next speaker now. So we've got Shabaz Chowdhury. If you're able to share your screen now, that would be great. It's going to be talking to us about the global dynamic network response of PC2 and PC3 waves to the 2015 St. Patrick's Day storm using supermag and intermagnet ground-based magnetometers. When your talk starts, I'll give you a warning when you're 10 minutes into your slot, if that's all right. Shabaz?
Has it disappeared?
Share your screen.
We shouldn't have. We should have just let him keep sharing the whole time. Yeah. Yeah. When you go, Shabaz.
So can you see my screen?
Not currently. I can see you talking. Have you pressed the share screen button? There we go.
Can you see?
Take it away when you're ready, please. Thanks.
Can everybody see it? So I'll just begin. So my talk's about the. So I'll be talking about the dynamical network response of the magnetosphere due to PC waves, and we will basically measure these PC waves using arrays of ground-based magnetometers. So we get our data from the supermag collaboration and the intermagnet collaboration of ground magnetometers. And so, as far as we're aware, this is the first time we're studying PC waves using networks, and we will be looking at the well-known St. Patrick's Day event. So we'll be looking at the magnetosphere during conditions of extreme driving, so geomagnetic storms, and we'll be using 100 plus magnetometers, specifically around 122 magnetometers globally for this event. So I'm based at the University of Warwick. Supervisors Professor Sandra Chapman. So first a bit on PC waves. So what are PC waves? Martin basically explained a lot on what ULF waves are, so I'm not going to say too much about them, but I will say that PC2 waves are involved with ion cyclotron resonances in the ring current. And essentially, these wave-particle interactions can lead to redistribution of ion populations, which is why people are so interested in PC2 waves, because as you can tell, they'll modify the duration of ring current intensity, while PC3 waves arise at the Foreshock due to ion cyclotron instability. And so in this analysis, we'll be mainly looking at PC2 and PC3 waves. So what are networks? Networks are basically comprised of nodes and edges. Nodes are objects and the edges are the relationships between them. For example, you could have a flight path network, social media network with nodes being people, edges being friends. In our case, the nodes will be magnetometer stations and the edges will be determined from the strength of a cross correlation function, which I'll touch on next. So we can characterize the network using different parameters. One is degree, which measures the number of edges each node has. And network edges can either be directed or undirected, as you can see on the top right-hand side. Our networks are geographical, which encodes extra information into the positions of the nodes, because the nodes are magnetometers, magnetometers placed on the Earth globally. So how do we make these magnetometers? How do we make these networks using this global array of magnetometers? So this is how we do it. So this is how we create an edge between two stations, and then we can repeat that process between every pair of magnetometer stations in the network to create a global network. So what we can do is we can take a window of a section of two magnetometer time series. Next, we can bandpass filter to extract the PC waveforms that we want. In this case, we want PC2 and PC3. The benefit of bandpass filtering is that it removes any nonlinearity from the data. It removes large, slow-moving trends in the low frequencies, and it removes noise in the high frequencies. So it does a lot of the data cleaning for us. So next, what we can do is we perform a cross correlation. Once we've obtained our PC waveforms, using the cross correlation, using the peak of the cross correlation closest to 0 and the sign of that peak, the sign of the peak of the cross correlation, we can determine the direction and the type of edge of the network if it is above a threshold. So if this peak at the bottom is above a certain amplitude, then we can form an edge. And I'll touch next on how we define whether the edge is directed or undirected, because we'll have different networks, both for directed and undirected. So we'll have directed PC3, PC2 and PC3, and undirected PC2 and PC3. So the direction is determined from the lag of the cross correlation. So if the lag is at 0, that shows that both of the signals are instantaneous. And if the lag of the cross correlation is not 0, it shows a leader and follower relationship between the two signals. So we can define a direction between magnetometer station A and magnetometer station B. So now let's move on to the event that we're analyzing. We're looking at the St. Patrick's Day storm. Here are some geomagnetic indices for the event. We have SME, which is measuring the auroral electrojet, and we have SMR, which is measuring the ring current. And here are the different sections, so dayside, noon, and dusk. And we also have our magnetic field quantities, and then our dynamic pressure from the sun. So we're focusing on 2 times A and B, storm sudden commencement, and then SME enhancement. So if we look at the station coverage for our event, we can see that we have a lot of stations in Canada, North America. Basically, that's just where most of the magnetometer stations are. And we have a few in Europe, and then we have sort of stations dotted around globally. And you can see different views of the Earth. So here we have our network analysis. So I know it's a lot to look at, but I'm gonna basically go through each plot slowly. Essentially, what we are doing, we are measuring the degree distribution. So how the degrees are distributed at every time. So at every time window. And essentially, what we can see is at A, for our PC2, for our directed PC2 network here, we can see that the distribution, the purple ones, for all the connections is responding. The distribution widens in response to the storm sudden commencement in A. And then we can basically see that at B, you sort of have a bifurcation of populations. You sort of have a population which is more connected. We know that's Canada and North America. And then we have another population which shows us our global connections. And essentially, that's the benefit of using these networks, is they can tell you what's happening at in different scales, locally and globally, and tell you how the coherence is changing over time. So the orange connections here are connections larger than 9 hours in magnetic latitude. So if we just count the number of long-range connections, we can see how these vary. And so we can basically look at local and global response to this St. Patrick's Day event. Below for PC3, we can't see as much response. It's something we still have to look into. Another thing to note, and is part of ongoing work, is the lag distributions. So how the lags are distributed at these two times are not symmetric, which is showing that energy is sort of moving through the system, because you have waveforms leading and following. And so basically stuff is moving around. And so you can see that at the bottom, you have the PC power, and you can see that the network degree distribution is not just tracking PC power, it's telling you a lot more about the system and what's happening on local and global length scales. So if we look at just the long range connections, you can see that this sort of bifurcation that we're seeing in the purple plot is not as obvious. There's still some connections, but it allows us to sort of compare length scales, just to reiterate that point. Okay. So I have a video here, and we can look at how the network is evolving at storm onset, and the color of the size of the nodes reflects the number of connections present, and you can see how they just start to light up at storm sudden commencement. And here you can just see how these stations and the network is spatially distributed during storm sudden commencement.
10 minutes into your start.
Here you can see SME enhancement. So here's the time B, and you can see that basically you can just see a lot of stations around North America, which is on the night side, which is why we think it's responsible for the bifurcation you see in the PC2 distribution plots. So summary. So I guess the key points are is the network degree just doesn't track the PC power, indicates a coherent response over a spatially extended region, and propagation of a spatially coherent signal. Basically, you see at onset, you see a response in the PC2 network, in the PC2 directed and undirected networks. And you also see this bifurcation, the changing behavior between global and local scales in the network. What we are working on now is to characterize a network with a few parameters. For example, looking at the evolution of this St. Patrick's Day storm and using the network to look at, for example, the variation between long range and short range connections to sort of characterize the system. And yeah, that's my talk.
Thank you very much for that. We're running on to our next slot, so we've got time for one very quick question, if there is one.
Yep, there's a quick question from Li Jen Chen. It's, do you see a difference between the stations located in the cusp and those outside of it?
Right now, we're looking at sort of everything. We're not sort of, we're not comparing different regions. We're trying to look for more. I mean, it's something that we can look at, but we haven't looked at yet. So it's something for future work.
Thank you for answering that question, Shabazz. If there are any more questions, please type them into the chat or something. Maybe we'll be able to answer them in there. So if we could move on to our next speaker now, Dr. Hongyang Zhao. If you could share your screen, please. Thank you. It's going to talk to us about magnetospheric responses to solar wind PC5 density fluctuations from 2D hybrid Vlasov simulations. So please take it away when you're ready. Thank you.
Yeah, thank you. Let me share it again. Yes, can you see it? Nice. Okay, yeah, I'll start. Yeah, so hello everyone. My name is Hongyang Zhou. I'm a postdoc working at the University of Helsinki. And today I'm going to share you about our recent progress using a simulation to study the solar wind imposed PC5 range density fluctuation using a 2D hybrid Vlasov model. Yeah, so the big question we're going to ask is, how does the solar wind variations affect the plasma properties in the magnetosheath and magnetosphere? And the way we're dealing this is with numerical experiment with velocitator. So first of all, what is velocitator? Velocitator is a collisionless hybrid Vlasov plasma model, showing on the figure here on the left. So basically, we are directly solving the Vlasov equation for each ion species. And in this work, we only include protons. As for electrons, we treat it as a massless fluids as a normal hybrid model. And in the generalized Ohm's law, we're solving up to the electron pressure gradient term. And here we set a 2-dimensional in space and 3-dimensional in the velocity space. And what's new here is that now we have the capability of having a time-varying Maxwellian boundary through the upstream boundary. So now this allows us to set a more realistic solar wind condition and study the time variations. So here, what we're doing that we set the base condition, density equals to 2 mu per cc, velocity equals to 600 kilometers per second, slightly higher than usual, and also a slightly higher temperature, 5 times 10 to the 5th Kelvin. We set a purely southward IMF with BZ equals to -5 nanotesla. And then we introduce a perturbation in the density with the amplitude 1 and a period of 150, which is on the lower end of the PC5 range. And this gives us an average alpha Mach number of 7.8, which is close to the average observed at Earth's magnetosphere. So first, we run this with the quasi-steady state in the XZ plane for 400 seconds. And then we introduce this sinusoidal density pulses as described previously from the upstream boundary on the right and continue the run for more than 3 periods. And here you can show that as time goes on, the density variations propagate all the way inside the sheath and creates this high density stripes within the magnetosheath region. And then it will propagate further inward inside the magnetosphere. So here are some results. So first of all, let's look at the global view. Here I showed you 6 panels of various plasma moments, as well as the electric and magnetic field components. And again, we see this clear density stripes all the way across the magnetosheath. Here at t equals 900 seconds, we can clearly see actually 3 within the sheath, and the 4th one is about to reach the front of the Foreshock. And meanwhile, we can identify this high frequency mirror mode and proton cyclotron mode that's triggered by the pressure anisotropy inside the sheath. And also, we can see these transient ball waves that are the fast mode signals coming from the reconnection at the magnetopoles. Then if we look at selective virtual satellites, so here I showed you 4 from 4 different regions. In panel A on the upper left, this is where it always locates within the upstream solar wind. And we can see that plasma propagates from the upstream boundary to this location. There's about 5% decrease in amplitude for the sinusoidal wave due to the numerical diffusion, which is, I think, tolerable. And then in panel B here on the right, this is a location where it crosses the Foreshock not once, but twice due to the density or pressure variation that's imposed from the upstream. And then in panel C here, on the lower left, this is a location where it's always inside the center of the magnetosheath. And we can see this 2 density peaks that's moving at the bulk plasma velocity, together with these high frequency oscillations that's from mirror mode and ion cyclotron mode. And last but not least, here the panel D, this is a location that's always within the magnetosphere. And this, you can clearly identify the 3 density pulses, which are not the same as in panel C. And these are actually the signals from the fast magnetosonic mode, which I'll describe more detail on later slides. So if we look closer at the satellite location within the sheath, we're trying to see if we have a theoretical agreement with our expectation. So here in our 2D XZ plane simulation, we should be able to get 2 modes. So the first one would be the compressional magnetosonic mode, traveling in the X direction, and here showing on the upper panel here, the perturbation of BZ versus EY. And we would say that this is a relatively clear signature of an anti-correlated perturbations. Whereas we may also expect a toroidal mode or the alpha mode that's propagating along the field. And here along the subsolar line, it will be along the Z direction. So we're checking the BX versus EY perturbation. And we will say it might not be so clear. And if it does, then it will still be a mixture of coupling with other wave modes. And then from another perspective, we look at the various quantities along the subsolar line at a given snapshot. So here I'm showing you T equals 850 seconds. And again, we can identify this density pulses that's moving at the bulk plasma speed and the mirror modes perturbation all the way basically everywhere within the sheath region. And here, so if you look at the velocity Vx component, for example, it's all negative, meaning that this is during a compression phase of the magnetopoles that's caused by the upstream density variation. And also the high density here, that's the high pressure here, that's related to the flux flow generation. And to incorporate the time information, we do this space-time analysis. So still the x-axis here is the x coordinates along the subsolar line, while the y-axis are the time within the time varying runs. So here we can clearly see the disturbances of the Foreshock as well as the magnetopoles. And there are various wave modes, especially within the magnetosheath. So first, we may see that the most striking one would be that's moving with the bulk plasma speed, and those are meaning that they are stationary in the plasma frame with the anti-correlated density and magnetic field, and these are the mirror mode. And we also have the fast magnetosonic mode that's caused by the upstream variation, and it's generated at the Foreshock, propagating downstream, as shown here as the purple dots. and it gets reflected back at the magnetopause and creating this backward, sunward fast mode. And when these encounters the density pulses that's moving at the bulk plasma speed, it will cause this enhancement of density that's showing in this density color contour. And also, if you look at these plots really closely, there are these high frequency image modes that can be shown here, like these more or less horizontal oscillations. Yes, and if we look close near the magnetopause, we can see this this transition from left to right, so 800 seconds to 850 seconds. That's from the expansion phase all the way to the compression phase. And it may alter the reconnection signatures as these imposed variations come in. And as a summary, so in this report, we report our progress in implementing this time-varying boundary condition for this hybrid Vlasov model. And using a 2D global magnetosphere around, we study the influence of this varying upstream density, and that creates this various wave mode propagation within the sheath and the magnetosphere region, and their modulations to those things, led primarily by the fast modes. And thank you for listening.
Thank you for that lovely talk. Has anyone got any questions?
Yeah, so there's one in the chat from Martin. It's quite a long question, so bear with me while I read it out. And you can also probably look at it yourself in the chat. But very interesting work. These are 2D simulations which can suffer from plasma pileup near the subsolar magnetopause, correct? To what degree do you think the structure of the phase fronts in the magnetosheath and magnetospheric signatures might be affected by this, and how results from the new 3D capability of Lassiator might differ?
Right, yes, I agree that there are these obviously 2D limitations to our run. For example, so if you go back to this slide, you can clearly see that the slow drift of the Foreshock. So clearly we are even not in a real steady state as in the 3D MHD runs shows. And but since we have a reconnection in this run, so the flux pileup may be that severe issue near the magnetopause. But obviously our next step would be trying to move on to the 3D configuration and to see if we can get more realistic pattern compared to the MHD models.
Brilliant.
Yeah, thanks. That's everything from the Q&A for the minute. I would ask a quick one, but I don't want to jump in if we're...
No, go for it. We've got a couple of minutes before the next talk. So if you want.
Could you go back to your virtual satellite signatures, please? I just wondered if when, yeah, here. So no, sorry, the next panel on. The next slide on, please. Yeah. So here, the bottom one strikes me that it might be if you're looking at BX, that could be the X component of the fast mode signature, and then it would kind of align, rather than being just indicative of the Alfvén wave, it could be the X component of what your fast mode would be, which kind of seems to line up with what's in the above panel, if I'm interpreting that correctly. So I don't know if you thought about that interpretation of it rather than solely as an Alfvén wave.
I think you might be right. So I'm not entirely sure about this, whether or not it's really Alfvén mode. Maybe it's just the BX perturbation that's due to the fast mode signature.
Okay, yes. Cool.
Oh, brilliant! Thank you. So I think it's time for our the final speaker of this this session, Lucille Turk. If you're able to share your screen now, that would be great. So she'll be talking about global hybrid Vlasov simulations of Foreshock waves and their transmission into the dayside magnetosphere.
All right, thank you. I see my laptop on. Oh no, my laptop starts to freeze. I turn off the camera because. Yeah.
If you're having trouble sharing, we could. I think Tom's got a copy of the slides.
Yeah, I think the sharing should work. I just hope the laptop will not crash during my talk. Or I got a slightly older laptop trying to get a new one, but it's taking time.
No problem.
So now you should see the presentation in full screen.
Yeah.
All right.
Oh, actually,
No, it's not.
in the presentation.
Yeah. Okay. Now it's in presentation
There
mode.
we go. Brilliant.
Okay. Sorry about that. Hello, everyone, and yeah, thank you to the organizers for putting together a very interesting meeting today. In this talk, I'm going to present some more recent results from the glaciator model, this time focusing on waves originating in the foreshock. So a brief reminder that the Earth foreshock is an important source of ULF wave activity in near Earth space. It extends upstream of the quasi-parallel bow shock and is populated by shock-reflected ions. And the interaction of these backstreaming ions with the solar wind creates a variety of ULF waves, and in particular the so-called 30-second waves that are fast mode waves generated by these ion beam instabilities. The foreshock waves, or these 30-second waves, attempt to propagate towards the upstream, but they are carried earthward by the faster solar wind flow. And it is thought that they cross the bow shock magnetosheath and enter the dayside magnetosphere, where they are the main source of dayside PC3 wave activity, so waves with period ranging from 10 to 45 seconds. There's a lot of observational evidence that these two wave populations, foreshock waves and PC3 waves, are connected, in particular because their periods depends on the IMF strength in the same manner. But there's also a lot of open questions regarding how they can transmit, and also how the other parameters like the wave power will depend on the solar wind parameter. And so in this talk, I'm going to concentrate on this latter part. What's the influence of the solar wind parameters on the wave properties? To investigate that, I'm using global simulations performed with the glaciator model. So Hong-Yang already introduced glaciator, so I'll just briefly repeat that this is a hybrid Vlasov model that is designed for global magnetospheric simulations. So hybrid Vlasov means that ions are treated as velocity distribution functions, while electrons are a charge neutralizing fluid. So in the model, we describe ion kinetic processes, and that means that foreshock waves are self-consistently generated in the model. So that's the major difference here for those waves compared to MHD simulations, where you cannot generate the foreshock waves, or upstream wave, as they're usually called, for magnetospheric ULF wave studies. And in this work, I'm using a set of 5 different glaciator runs that have different upstream conditions. All of these runs have completely steady solar wind conditions, so all the perturbations are self-consistently generated and mostly in the foreshock. And all these runs are 2-dimensional, covering the equatorial plane of near-Earth space. So that means when I'm talking about PC3 wave activity, I mean compressional waves, compressional PC3 waves, but not the field line resonances, because they are not described in a 2D setup. So now some overview of these 5 runs I'm using for the comparative study. So 3 of those 5 runs have an oblique IMF configuration, about 30 degrees from the Sun-Earth line. 2 of the runs that are shown here on the left have exactly identical solar wind parameters, with the exception of the IMF strength. And as a result, we get different alpha and Mach numbers in the 2 simulations. And then there's a 3rd run with a similar IMF orientation, but quite different parameters. It's like high driving solar wind conditions with high density, high magnetic field strength, and that corresponds to actually an ICME interacting with near Earth space that we studied for another investigation. And then 2 more runs that now have a quasi-radial interplanetary magnetic field almost aligned with the Sun-Earth line. And again, identical parameters in the 2 runs with the exception of the IMF strength and so the alpha and Mach number. So because of the quasi-radial IMF orientation, you can see the Foreshock waves, the Foreshock extending upstream of the subsolar magnetosphere in the 2 simulations. But also what we can see right away from those plots is that by just changing the IMF strength, we get very different Foreshock wave properties. In particular, the wavelength is much shorter at larger IMF strength as was expected. But those changes are also reflected downstream in the magnetosheet, where we get smaller scale size of the fluctuations and also less turbulence or lower amplitude fluctuations in the dayside magnetosphere. As a validation of our runs, we compare the wave period in the Foreshock to predictions from 2 empirical formula that are widely used to determine the upstream wave properties as a function of the solar wind parameters. And we find a good agreement with this formula and also the same variation of a shorter wave period with larger IMF strength. Then we looked at the PC3 wave power in the simulation, and how this is calculated here is that we work as if we had a virtual spacecraft in each grid cell of the simulation domain. So for each grid cell, we have a time series of the magnetic field fluctuations on which we perform a wavelet transform. And from this wavelet power spectrum, we determined a mean wave power across the PC3 range and for 150-second simulation time. And we calculate, here I'm showing mean wave power, but we also tried median wave power or total wave power, and all those parameters gave similar distributions. And so we have again here our 2 runs with the quasi-radial IMF, and we see that we have significant PC3 wave power in the Foreshock. So that's correspond here to the transverse wave power, because we're looking at the BZ component out of plane. Inside the magnetosheath, we have the amplification of the wave power, some interesting fine structures near the subsolar point. And inside the magnetosphere, so now the BZ will correspond to the compressional wave power because the field is mostly along BZ. And we see that the wave power is largest near the magnetopause and then decays when moving inwards, which is what you would expect for wave power entering through the magnetopause. And if we compare this wave power with that obtained for the same run with a lower Mach number, we have here exactly the same color bar for the 2 plots. So we can see right away that the wave power is significantly lower at lower Mach number. And that's the case not only in the Foreshock, but also in the magnetosheath and magnetosphere. To quantify this variation, I'll simply divide the map to the left with that to the right to obtain this plot here. And we see that we have a wave power that's about 10 times larger in the simulation with larger Mach number. The reason for this is most likely because at larger Mach number, the shock is stronger and reflects more particles. So we get a larger density of suprathermal ions across the Foreshock. And in turn, that increases the growth rate of the waves. And that's why we get this larger wave power in the Foreshock. Interestingly, this is also reflected in the downstream region, so that further supports that there is a direct connection between the Foreshock waves and the waves in the dayside magnetosphere. One place where it's interesting to look at the wave power is along the magnetopause. However, determining the magnetopause position is always challenging, whether it's in spacecraft data or in numerical simulations. And here we use a proxy of the magnetopause that was proposed by Brenner et al. In 2021 that they applied for global MHD simulation. and they use an isocontour of the beta star parameter, where beta is almost like your typical beta parameter, except that you take into account the dynamic pressure in addition to the thermal pressure to calculate it. And so we found that an isocontour of beta star equals to 0.15 correspond reasonably well with the magnetopause position. And so we extracted the wave power along this isocontour in all of the runs to obtain this plot here of the wave power as a function of magnetic local time. So the plot is quite busy, but the first thing I want to highlight is that the wave power can change by several orders of magnitude depending on the upstream solar wind conditions. If we look again at our two runs with the quasi-radial IMF, we find again this tenfold increase in the wave power entering the magnetosphere at larger Mach number. Then we had another set of two runs with this time oblique IMF orientation and different Mach numbers. And again, we have a variation, almost tenfold variation in the wave power for different Mach numbers, but that's true only on the dawn flank where the foreshock is located. On the dusk flank, we have a huge decrease of the wave power in the higher Mach number run, but not so much of a variation for the other run. So there's three possibilities to explain this. One is that because the bow shock shape is flatter at lower Mach number, the foreshock extends more towards positive y direction, and so we get more wave activity into the afternoon sector. Another possibility is that the foreshock waves are weaker at lower Mach number, so the difference between foreshock flank and non-foreshock flank is not that pronounced. Or maybe it's our magnetopause proxy that isn't working so well. So to remove this possibility that it's an issue with the magnetopause proxy, we took the wave power at a constant radial distance inside the magnetosphere, here at 6 Earth radii. And so we do see still the dawn-dusk asymmetry for the higher Mach number run and a weaker asymmetry, but still some asymmetry at lower Mach number. And so showing that most likely the asymmetry is reduced at lower Mach number, but it's still there. So to conclude, we have used a set of 5 global hybrid Vlasov simulations from the Glaciator model with different solar wind conditions. And we found that the foreshock wave power increases with increasing Mach number, as could be expected, but now we have also quantified this variation, and this change is directly reflected in the change in PC3 wave power inside the magnetosphere. We found dawn-dusk asymmetry at oblique IMF orientation, again as expected, but this asymmetry reduces as lower Mach number, and those changes further support that there's a direct connection between PC3 wave power in the dayside magnetosphere and foreshock wave power. And thank you for your attention.
Thank you, Lucille. Has anyone got any questions?
Yeah, we don't have anything in the Q&A just now. I think we've got a couple of minutes till the end of the session, so if someone would like to type something out, we do have time for it. Otherwise, we could come back to it in later discussions. But yeah, there's nothing in the Q&A just for now.
I have a very, very quick question. I like the sort of correlation between the Mach number and sort of like the scale sizes and the amplitudes of the foreshock waves. Have you thought about trying, or if it's possible, that is, thought about trying this for a really sort of low Mach number case, like you would get at, say, Mercury?
We haven't gone to dramatically low Mach numbers. Like the lower Mach number run we had was this one with 3.4, but it would most likely reduce again the wave power until it almost disappears, like on the observations that were made on the day the solar wind almost disappeared, when they noticed that there was no PC3 wave activity on that day, even though there was a very weak foreshock. So I expect we would see the same thing.
Cool, thank you.
Can I just ask one quick one as well? If we have 1 minute. I realise we're at the time, but it's just also just showing my naivety to or lack of understanding of the foreshock in general, I guess. But if would you also have this for a lower frequency? So with this, you're presenting here stuff on PC3. Would you see similar for say PC4, PC5?
So you could reach the PC4 range for the foreshock waves if you have a very low magnetic field strength. But then the period of the waves is really determined by the interaction. It's a fraction of the gyro frequency of the particles. So then if you go to PC5 range in general, it's not due to the foreshock waves, it's another source in the solar wind, for example, density fluctuations that Hongyang presented, or then there's transient processes in the foreshock that disturb the magnetopause and cause PC5 waves inside the magnetosphere.
Okay, thank you for answering my simple question.
Right, thank you. So I'd like to thank the speakers in our first session. So we're going on to a short break now, due to return at 5 to 12. So just under 15 minutes time. I think Tom's chairing the next session, so he might want our speakers for the next session to stay back briefly. I'll hand over to you, Tom, actually.
Yep, no worries, thanks, Matt. Yeah, everyone feel free to disappear, get a cup of tea, and yeah, we'll be back at 5:02. If the speakers for the next session want to either hang around just now or drop in with 5 minutes to go, feel free to. I'll bump you up to the panel and we'll test out the screen sharing. But apart from that, I'll see everyone in 13 minutes. Thanks very much. Okay, well, in order to keep time, Matt has kept time so well in the last session, I better do the same. So we're going to get started again here, it being 5:02. I'll introduce our first speaker, who is David Southwood. So if you'd like to start sharing your screen, David, who's going to be talking to us about how can you detect field line resonances, or the detectability of field line resonances. Again, if you've got questions, please just put them into the Q&A or the chat. I see the chat's being used for that as well. That's great. And Claire will endeavour to read out your questions when the time comes. But with that being said, David, over to you.
Right, thank you very much, Tom. Good morning, it's almost good afternoon. On the detectability of field line resonance, that's a detectability on spacecraft, but we're going to use simulations in order to look at some of the problems that's associated with. Okay, the inspiration of this is the final orbits of the Cassini spacecraft, which were polar orbits that passed within the rings of Saturn, planetward of the rings of Saturn, and down in the corner, in the right-hand corner, you can see an example of highly azimuthal polarized magnetic signals seen as the spacecraft came across the D ring, that's the innermost ring, peak amplitude after you've passed over the D ring in a cavity inside, and then you go through the equator and see the same signals as you exit through the same L shells in the southern hemisphere, having entered in the northern. So quite naturally, I think, those look as if one has Alfvén waves that are azimuthally polarized, and what's going on is the field lines are oscillating azimuthally. They're very highly polarized in the azimuthal direction. And the question then, of course, is, since they're indubitably Alfvén waves, they're quasi-sinusoidal, So they'd be standing waves, presumably with the fundamental structure along the field line. What are they? Well, the notion put forward by Southwood and Company a year ago was that they were being pumped by eigenmodes of the whole system, exciting alphane waves in this high density region, high plasma density region. It's actually the topside ionosphere, effectively, of Saturn inside the rings. So the simulation I'm going to look at some properties of the standing waves, the field line resonances, or FLRs, using the simulation. The model in question is the Wright-Nelston model of 2020, and it's based on a background dipole field. And the field line resonance, the fundamental field line resonance frequency varies in the equatorial radial coordinate, that is the magnetic shell coordinate, as you see there. So omega A is the alphane resonance frequency, and the driving frequency is chosen to be a global eigenmode frequency. And so there are going to be 3 field line resonances in the simulation that you'll see. And here is the high density cavity, the sort of thing we think we're flying through with Cassini. So here goes the simulation of the growth of the field line resonances. They kick in, our damping is fairly high. It's numerical damping, but it effectively means that after about three cycles, you have a fairly steady situation. If I just stop at that point, one thing that is quite clear is that the field line resonances phase lock once they've set themselves up. And that's something I actually hadn't realized, but the minute you think about it, it's obvious. The field line resonance is absorbing magnetohydrodynamic energy from the fast mode, from the eigenmodes of the whole system, and they will phase lock simply because they will absorb energy equally once you've got to steady state. They don't exchange energy after that point. Okay, there are 3 resonances, and the other thing you can see clearly is differences in amplitude. And the difference in amplitude is more or less controlled completely by the gradient in the alphane frequency. So where the gradient is largest, the amplitude is smallest. So on the edge of the cavity here, you can barely see the resonance. It's being swamped by the large resonance immediately inside it. Okay, you could also see clearly phase motion in the resonances. You could see the signals moving outwards or inwards. The sign of that, whether it goes inwards or outwards, is simply proportional to the gradient in density, the gradient in the alphane frequency. And the reason for that is the structure through resonance. If we use a complex representation going through the resonance, the spatial structure, at the resonance, there's the peak amplitude, but elsewhere, it's in the imaginary part that the amplitude is dominant. So there's a change in phase through the resonance, a change in phase of pi. The direction of the change in phase depends straightforwardly on the sign of the gradient of the resonant frequency. So the spatial phase is there if you were in the plasma frame, but the spacecraft isn't in the plasma frame. The spacecraft is moving through, and so it will see this spatial phase variation as a Doppler shift. So here's what lessons to be learned. Saturation, not particularly interesting here, except that we hope our waves are saturated, and I'll come to that later. The amplitude and width are proportional to the inverse of the gradient in the local field line resonance frequency, omega A. If more than one resonance is present, they phase lock, and energy is preferentially absorbed in the resonance region. That's why they're resonant. The energy transport's associated with the phase motion, and the phase changes by up to plus minus pi across the resonance. So the consequence of that is, in steady state, there's always apparent phase motion, and that phase motion will appear on a spacecraft as a Doppler shift. And what does that mean? Change of frequency, apparent frequency, and the Doppler shift will reverse between outbound and inbound as you pass through each resonance, because the phase motion is systematically outward or inward at each resonance. In fact, it depends how rapidly the spacecraft travels through the resonance. So in the top sketch, I've shown the idea of going fast through the resonance. Then you will simply get a phase flip at each of the resonances going in and out. However, more interestingly, if the time taken to travel through is of order the period of the wave, then the wave frequency is dramatically changed. The phase changing by up to pi means the frequency can apparently change by up to 50%. And you will get structures where the regular frequency changes dramatically to doubles, or goes up by a factor, goes down by a factor of 50%. In fact, as we'll see, the Cassini FLR encounters are slightly less extreme than this. The transit through appears to be about in 2 periods. Okay, there are some model orbits to take us through, and the green dots and the purple dots indicate resonances, and we're going to fly a spacecraft on a polar orbit cutting through the high density cavity. So that's the 2 innermost resonances. In fact, we've chosen this so that we get travel through takes, the speed of the spacecraft is of order the period of the wave, so we get the most disruption to the periodicity. And look, going in here, the waves are traveling out towards us. So the period is shorter than the guide wave, which is showing what the period is in the plasma frame, and traveling outwards, the signal broadens as the period is increased. And the second resonance is almost swamped, but you can see it on the way out. You can't see it on the way in because of the scale of the inner resonance. Here you get the step change, saying that you travel through the resonance in less than a period. So everything there fits, but of course it doesn't fit with the data. So let's take, it was the very sinusoidal nature of the Cassini signals that suggested they were standing Alfvén waves. To detect if field line resonance is going on, you need to know where the signal departs from being purely sinusoidal.
About a 2-minute warning, David.
Okay, the experience of the analysis, we make the following hypotheses based on the by our simulations, and the spacecraft, we assume that the whole signal is coherent in the plasma rest frame. There's at least one resonance, and the transverse signals are north-south antisymmetric, as we've observed anyhow, and the cycles on entry and exit are non-resonant. Here is one of our orbits. If we take the low frequency band, you'll see actually no resonance. In fact, apart from near the equator where it's so complicated to interpret, the signal switches from being in phase in the north to being out of phase in the south. There's a 300-second guide wave, and that's more or less what you see on the spacecraft. It means the spacecraft did not get deep enough into the cavity to detect resonant effects. However, let's take shorter period, higher frequency, and here we use our rule to say, take it in phase on the way in and out of phase on the way out. This is the highest frequency that we can do this for this signal. And hey presto, you'll see that there's a drift between the signal measured, the black, and the guide signal, the red, both inbound and outbound. In fact, the resonances are somewhere where those arrows are, lasting a couple of cycles. In fact, this also shows that the signal outbound is moving through a gradient that's opposite to what we had originally assumed in our simulations. It also means we've got to reassess the southward work of last year. There we deduced, apparently in the peak amplitudes, 176 seconds, but it didn't match the oscillations outside. Let's now assume this is the whole, we're seeing the whole signal all the way through, and we're going to have to change the period. And we use the rule to say the signals on the outer region are out of non-resonant, so that they measure the same frequency in the plasma frame as on the spacecraft, and that they switch from being in phase to being anti-phase as we exit. That's a wave of 140 seconds fits that condition, and hey presto, you see where the amplitude was biggest. We're seeing the phase drift, which is entirely consistent with passing through a resonance. In fact, you can see that the signal passes from in phase to strictly an anti-phase here, exactly a change of pi in the phase.
Last minute, David.
Okay, there we are. There are the resonances, and that's exactly where the amplitude is maximum. So I think we've tested the Cassini data, and somewhat to our surprise, we found we got it wrong in the paper published last year. It's much more subtle, but on the other hand, we've got a recipe for interpreting what we saw then. In particular, this signal phase variation in space is very important as the spacecraft travels through resonance. Thank you for listening.
Thanks very much, David. Claire, have we got any questions come in, or are we?
There are no questions currently in the Q&A.
Yep. I mean, I could ask one, but I mean, I'm a bit biased on this work. So,
Chair's prerogative. I think you should.
Yeah. Okay. So okay. Just in a quick one, quick minute or so. For this, we've sort of assumed, we're assuming we've got this driver, and that, okay, for idealized purposes, we're taking that to be a constant frequency here. Are there any observations of like global modes at Saturn? Like where is Cassini flown, say, outside of where it flew for these proximal orbits? And is there any sort of good observational data of fast modes out there?
I don't think anyone's really looked. So there's been a lot of interest in the very low frequency signals in the MHD range associated with the rotation of the planet. It's a fast rotating planet. Then there's a lot of interest where the strongest field line current in the auroral zones, with sort of around 100-minute oscillations, sort of around an hour or so, associated with communication between the equatorial plane and the ionosphere. I don't think anyone's made a serious study, I certainly haven't, of potential global modes, of, in fact, compressional signals. There's an enormous amount of Cassini data. I mean, it's 13 years worth at 1 second resolution. So there's.
So basically, what you're saying is we could look at it. Is what you're saying?
Yeah. No, I think it's conceivable. Yeah.
Okay. Well, thanks for that, David. We better move on, otherwise I'll be running over on my session. But thanks very much for that. And okay, so next up we have Matt James, one of our organizers as well. who's going to be talking about looking for 3D field line resonances in ground-based data. So over to you, Matt.
Thank you, Tom. Can you see my screen all right?
Yes, I can indeed. Can see your cursor as well.
Excellent. Right, so before I begin my talk, I'd like to just acknowledge that there is an ISI team led by Andrew Wright that's actually looking at 3D field line resonances. And I was fortunate enough to take part in their meeting last year. And this is why I'm trying to find one in ground magnetometer data. So before I talk about what 3D field line resonance sort of is, let's have a look at the sort of classical picture of a terrestrial field line resonance, 2D resonance, if you will, I think. So they are driven by sources external to the magnetosphere, such as by solar wind buffeting on the magnetopores. This sends magnetosonic waves inward into the magnetosphere, where if the local eigenfrequency is matched by this, the frequency of this magnetosonic wave, you can set up and excite field line resonances. Now, if one was to consider the inner magnetosphere as being approximately to a first order a pure dipole, and these field line resonances would oscillate toroidally, so that is azimuthally around the planet, as a global shear Alfvén wave, which is confined to a single L shell. Now, in the case of a 3D field line resonance, this is a bit different. So real magnetospheres are not axisymmetric. So actually, they're not dipolar fields purely. So these field line resonances may actually cross L shells and as a result exhibit non-toroidal polarization angles. One example in the Earth's magnetosphere where one could expect to see such a 3D field line resonance would be in the presence of a plume. So I've stolen these plots from a recent publication by Elsden and Wright, I believe published last month. The plot on the left shows the Alfvén speed, and you can see there's a nice big bite taken out of it here. This, I believe, is to represent a density enhancement due to the plume. And the plot on the right shows the simulation of a resonant event, and you can see that we have a nice azimuthal, sort of toroidal field line resonance set up over here, and then in the presence of this plume, you see that actually there are some non-toroidal components to this resonance, and these little bits are the bits that I'm interested in finding in real data. To do this, I'm currently looking at ground magnetometer data from the image network and from the Charisma network. I'm also incorporating electron densities as measured by the emphasis instrument on both of the Van Allen probes. So this uses the upper hybrid frequency of the plasma to determine the cold electron density. The reason I'm doing this is because if there are large jumps or drops in the electron density, these could be due to the spacecraft crossing a boundary such as that of the plasma pores or into or out of a plume or some detached plasma, which is exactly where we want to look. What I'm doing with the ground magnetometer data, so I'm doing two things. If we look on the left of the slide first, if we take a single ground magnetometer, we take all three components of the magnetic field as measured by that ground magnetometer. We do spectral analysis on that data with a sliding window. We obtain power spectra similar to this on the middle panel. The little green dots just show the sort of the peak in the wave power for each spectrum. If we take those spectra from each of the three components, we can then use those to calculate polarization parameters such as polarization handedness, polarization eccentricity, and polarization angle, which is basically what's being represented here in this bottom plot, where the colour represents the handedness of the polarization, and essentially each one of those is a hodogram of each of these little green dots in the spectrogram above. And the reason I'm doing this is because it might be useful in actually being able to work out if we're looking at a field line resonance. The other thing that I'm using these ground magnetometers for is crossphase analysis. So that's shown on the right here. This is using method by Wharton et al. 2018. So we take two latitudinally spaced ground magnetometers, we take the H component of those and perform spectral analysis on those, cross those spectra and calculate the phase, the cross phase. And basically we're looking for negative cross phase, because negative cross phase corresponds to the natural eigenfrequencies of the field line that sits approximately between these two stations. And what I expect to see, hopefully, is if this pair of ground magnetometers crosses over a boundary, let's say over into the plume, we would see a change in the natural eigenfrequencies that that the crossphase is showing. Hopefully. So, what might we see? So I just said about the crossphase. If we look on the left again, if we imagine that we're looking at a pair of ground magnetometers that sit on a field line that maps out somewhere in the equatorial plane, some L shell, in this case L of 4 for an example, we can imagine that with time will rotate around the planet and through. So if there's a plume, it'll start off in the plasma trough here with low plasma mass densities. It'll eventually cross a boundary into the plume, which will have higher, more plasmaspheric-like densities, and then eventually it'll pop back out the other side into the plasma trough. As a result of this, we expect the eigenfrequencies to change. So if we look at this plot here, it shows the first three eigenfrequencies of that imaginary field line, and we can see that they change substantially as you cross the boundary each time. So this is what I intend to use the crossphase analysis for. And then on the right, if we imagine that we've got a latitudinal chain of these ground magnetometers, we can look at the wave power and the wave polarization parameters. And we can imagine that if we're back in the plasma trough with this chain of magnetometers and there's a field line resonance present, the latitude at which the field line resonance is apparent, we'll see the highest wave power. We'll see linear-ish polarization, and either side of that we'll see presumably a reversal in the handedness of that polarization. And then as that sweeps around the planet and hopefully goes into a plume, we should then see that same frequency, in theory, but at a lower latitude, so because of the enhanced density. And then assuming all of that works, then we can look at this region near the boundary, across the boundary, and hopefully that is where we'll find evidence of this 3D field line resonance that I'm looking for. So first of all, to find these, I am finding the times where the Van Allen probes are actually in the right place, either mapping to image or charisma. I'll then establish whether there is a plume present using the electron density data. And then the stage that I'm currently at is trying to use the crossphase to work out when each magnetometer pair crosses this boundary. It's actually surprisingly difficult. And then assuming that works, then for each of those events that we've got left where we can work out where the plume is, we can see if there is a resonance and then try and find that 3D resonance that we're looking for. This is just one method that we're looking at the moment. So as an example, here is what looks like a plume crossing. So these top two panels show the electron density as measured by both of the Van Allen probes. At this time, they're both moving radially outwards in the afternoon sector, approximately. These green lines, the first two green lines in each panel show where they cross the plasma pores into the plasma trough. Then a little later on, both probes encounter a density enhancement, which looks like they are entering into a plume, and then a little bit later further out, they cross back out into the plasma trough. This is one of quite a lot of events that I'm reducing. I can't remember the exact amount. We can map that to the surface as shown in this plot here. So these are the spacecraft footprints. They're quite wobbly. That's just due to changes in the parameters that drive the Tiganenko models. And these little yellow stars that you can see are the boundary crossings that I just pointed out in green. I think it's actually more useful, to map these out to the magnetic equatorial plane, as shown in this plot here. So we've got sun at the top, dusk over to the left. I've shown these little yellow stars again. I've actually drawn on some completely and utterly made up hypothetical boundary lines just to so you can sort of see what I'm thinking. At this point, though, I think it's probably a good idea to include the equatorial footprints of the ground magnetometer pairs, like this.
About a minute to go, Matt.
Thank you. So this basically illustrates just how complicated this can actually be, because it's not that obvious whether most of these pairs even go near to any of these boundaries or not. A couple of them look like they should, they're likely to. Exactly pinning down when and where, that's difficult, but this is where I'm bringing in the cross-phase analysis. So here are some cross-phase spectra, some examples. The big dark blue blobs are basically the sort of significant negative deviations in cross-phase, which correspond to your eigenfrequencies. And we're looking for sudden changes in these. So we can see that, for example, in the top one, these are quite nicely laid out bands of frequencies, and all of a sudden it stops, something happens here. Exactly what is not clear, but in a lot of cases it's quite messy like these, so it's quite hard to tell what's going on. So thought I'd have a quick look at machine learning to see if that can sort of help. What I'm currently looking at, what I did a few days ago, was to cluster these cross phases, basically taking a bunch of cross phases, doing some dimensionality reduction, and then using the k-means algorithm for a bunch of different cluster sizes to sort of group them up into different sort of classes. The example I'm showing on the right shows the case where I've picked 4 clusters. It's not clear how many clusters I should use. I would assume there'd be at least 2. You know, one for the plasmasphere waves, one for the plasma trough waves, or something like that. But you can see that in this case, like, a couple of these classes show quite obvious eigenfrequencies. For instance, this one here with 12 and 36 megahertz, and some quite obvious sort of local time preference for some of these classes. Now, this is where I'm at the moment. I don't expect this to exactly work perfectly, because I don't think these data are linearly separable, which means that I'm going to have to try and consider other clustering algorithms. But hopefully, once I've finished this work, you know, this will give us some insight into where the plume is, and then find these 3D field line resonances. There's a lot more work to them. I will leave that there.
Okay, thanks. Thanks very much, Matt. I'm starting to realise what a thankless task we've given you by setting you on this observational journey of trying to find these things. Claire, were there any questions from the chat? Or are we?
There aren't any questions. I have one if we've got time for that.
Sure, yeah, we can go for it.
Sorry about. So Matt, is it right that you're trying to identify really like? Are you trying to identify the most negative crossfades, or a region of negative crossfades? I'm just trying to understand.
The negative crossfades, yeah. In a way, I'm not actually excluding positive crossfades in my clustering analysis, because I'm aware that the reason you have negative crossfades is due to the latitudinal dependency on the frequency. Now, if that ground magnetometer pair sits either side of a boundary, such as the plasma pores, then one could imagine that crossfades would be reversed. It would be a positive crossfades, which I would, I'm part of me hopes that there is a cluster, a very small cluster, that sits exactly on the boundary, which my machine learning will magically pop out and just say, this is the thing you're looking for. But I suspect it's not going to be anywhere near as simple as that.
And really quickly, is there any, would there be any benefit of attempting to use longitudinal, an array that is spread out in longitude rather than one that's spread out in latitude, given that these are 3D?
Yes. Yeah. We are also, and have looked at the longitudinal stuff. We've not done any crossfades on that, so I'm not completely sure what the meaning of that will be. Yeah, so we've looked at the polarization, we've looked at the wave power and stuff like that, and it's not entirely obvious what's going on. So we've tried a few different events with that, but yeah, I mean, that's something that once we've found one of these events, that will be the sort of the thing to do, is to look at the polarization and the wave power as a function of longitude as well.
Great, thanks.
Okay, thanks very much, Matt. Andy, if you want to start sharing your screen. So next up, we've got Andy Wright, who's going to be speaking about high M modes now, and how these colloidal alphane waves evolve in a dipole magnetic field. So, Andy, over to you.
Okay, I'm just trying to share my.
Yeah, I can see the screen.
Full screen.
And I can see your cursor. That's all good. Okay.
Yeah, thanks for that, Tom. Thanks for organising this session. So I'd like to continue this session's theme of looking at alphane waves. However, I'm going to be talking about colloidal alphane waves. So these are also referred to as high M alphane waves, M being the azimuthal wave number. So a key idea I want to get over is the idea of phase mixing, and I'll illustrate this to make sure it's clear to you with a nice example from classical mechanics. So if you look at the right-hand figure here, we've got a set of pendulums. They range they have different lengths. That means they're going to have different frequencies. And the left-hand panel is looking down on top of these as they swing back and forth like this. And you'll see that there's a variation in phase as you move in what I'm going to call the X direction. So I'll just play this movie. And if you perhaps start by looking at the right-hand side, you'll see how the pendulums drift out of phase, forming the snaking pattern. And then if you look at the left-hand panel, you'll see they all start in phase, and then phase structure starts to build up, and the wavelength in X actually decreases in time. And the reason for this is that we have the frequency of a pendulum depends on what I'm calling this X coordinate. And if you want to see more movies of this and actual real life examples or animations, just go to YouTube and search for pendulum waves. So I'll just show a few snapshots from that animation. So as we go from the top snapshot here, this is the early time down to a later time. And I've indicated with this yellow line here, the distance between two zeros in terms of this displacement up and down on the screen. And as you'll see, as time increases, the yellow line gets shorter and shorter and shorter. And that's associated with this phase mixing length. So the wavelength in X here, lambda X, you see its dependence here on the change of frequency omega with x. Also importantly, it goes as 1 over time. So although this is the wavelength in x, well, generally we just refer to it as the phase mixing length. And you can see the scaling with time, that it goes as 1 upon t, is why this yellow line here gets shorter and shorter as we go to later times. So let's think about what colloidal Alfvén waves will do. These were studied by Jim Dungy back in 1954, actually in a dipole field, but I'll use a cold plasma box model just to kick off to get some of the ideas over. So the diagram on the left, X is representing the radial coordinate, Y is the azimuthal, and I've got some lines shown in blue here representing the equatorial plane plasma velocity associated with the Alfvén wave, and this is just a snapshot. It would all oscillate with the Alfvén frequency. And the key thing to note is that the dominant velocity is in the x direction or radial direction, as will the plasma displacement and magnetic field perturbation associated with the wave be. And to get this sort of solution, you need to be careful about specifying the extent of the waves in the y direction, or like the wavelengths in y. That corresponds to the azimuthal wave number, which is large, so it's a small wavelength. And compare that with the length of the waves in the x direction. And to get this sort of high-end decoupled solution, you need this ratio Ly over Lx to be much less than 1. So you get these narrow ellipses aligned with the radial direction. Now, when you get that, you find that you can get the Alfvén wave frequency for these colloidal waves. It's given here, just depends on the parallel wave number and the Alfvén speed, which can of course depend on x. So what we're going to have is at this value of x, the waves will have one frequency, so they'll oscillate back and forth here with one period. At a different x, different frequency, they'll oscillate with a completely different frequency. And that's really just like the pendulum's animation we've seen. It means that as time goes by, you're going to start to build up sort of a decreasing wavelength in the x direction. That means that the effective scale in the x direction is going to decrease. It means that Lx is going to get small. And this ratio that we want to be much less than 1, it can't go on indefinitely like this. It's actually increasing as time. So what ends up happening is that we're going to violate this assumption we need for the colloidal Alfvén waves. And we'd like to know what happens when this system evolves and violates the assumptions required to have colloidal Alfvén waves. Well, that question was actually answered by Ian Mann in 95, again in the box model. And I've got 3 snapshots here from simulations that from Mann's paper. Again, moving from the top to the bottom through these rows, time increases. And the left-hand column is showing the displacement in the x direction or radial direction. So that's the colloidal Alfvén wave. And the right-hand column is showing the azimuthal or y displacement. And I've also indicated the phase mixing length here with the red line. So you see as time increases, it gets smaller. And it's also present in both the x and y displacements. Now, we start off at an early time with the dominant displacement being in the colloidal direction. So this is a colloidal Alfvén wave. But as time increases, that colloidal displacement decreases in amplitude. In contrast, the toroidal displacement actually increases in amplitude as time goes by. So this means we start off with a colloidal Alfvén wave here. We phase mix, something happens, it can't stay as a colloidal wave, and it converts to a toroidal Alfvén wave with displacement in the y direction. I've got vertical green lines here. They're at the same position in both left and right columns. They're centered on where the initial colloidal Alfvén wave is set up, and the final toroidal Alfvén wave is centered on the same field line. So we have this idea of a colloidal Alfvén wave. It oscillates and it rotates and turns its its polarization or its displacement towards the toroidal direction. And there are actually observations of this by Saris in 2009 from satellite data. Okay, so that was warming you up with ideas in the box model. Now let's go to a dipole field, and things are quite different in a dipole field. Dungy in 54 looked at the toroidal and poloidal frequencies and found that they were different. So I'm going to characterize the polarization with an angle theta. If theta's pi/2, then we have the poloidal frequency, and if theta is 0, that corresponds to toroidal. So what Dungy did is he looked at, say, this field line x1, and he concluded that you could work out for that field line the poloidal Alfvén frequency, which is this green dot, and for the same field line you could look at the Alfvén wave with a toroidal polarization, and he found that had a different frequency. Well, this was also generalized to outside of dipole fields by Singer in 81. And more recently, Tom and I showed how you could actually consider an arbitrary polarization between toroidal and poloidal, and you can work out what the frequency is, and it just changes smoothly from one to the other. And this ties in exactly with what the previous speaker was talking about, of having a polarization for your Alfvén wave that's not toroidal. It can have any polarization between toroidal and poloidal. So the ones Matt was just talking about, it could be inclined at, say, 45 degrees and have a frequency here. So when we start off with a poloidal Alfvén wave here on field line labeled x1, it's going to phase mix. It's going to start turning towards toroidal, but it's going to have to shift its L shell. So it can start off on field line x1 with this frequency given by the horizontal line. But if it wants to keep that frequency when it becomes fully toroidal, it's going to have to move over to field line x2. This is the same kind of curve for x2, but the density and field line length are different. So it's a similar curve to this, it's just slipped down because of the differences in density and field strength. But the key thing about this field line, it's special because its toroidal frequency matches the initial poloidal. So what we're going to expect to happen is that the field line will oscillate here as an Alfvén wave. It'll rotate and have to migrate out to this second field line where it can be a toroidal wave. Now, I'll show you a simulation for a 2D dipole that actually shows this feature very clearly. Again, we've got 4 snapshots, increasing in time as we go from top to bottom. The color in this contour plot is showing the size of the velocity perturbation in the equatorial plane. And we can begin by seeing some of the features I've alluded to. You can see we start off with a scale in the x direction here that's relatively large. And if we just jump to the bottom panel, the scale in the x direction, that's between 2 red ridges, well, you can see that is greatly reduced, and it decreases in time as the phase mixing length as we move down through these panels. We can also see that the poloidal Alfvén wave started off here, and then at the finishing time, it's no longer centered on this vertical dashed black and white line. It's actually migrated over to clearly a different L shell. And this property of field line of Alfvén waves migrating across L shells was something suggested by Leonovich and Mazur and Klimushkin in the 90s. You may like to think, how can an Alfvén wave do this? Because we've heard in previous talks that Alfvén waves propagate along field lines, but here they're also migrating across them.
About a minute or so, Andy.
Okay, thanks, Tom. The plasma velocity associated with the wave is basically aligned with these ridges. So in the top panel, it's completely poloidal. Then as we move down, it's inclined like this, and I'm showing that in this just to the right of the colored panels. And as time increases, it rotates from the poloidal orientation down towards the, this isn't all the way to toroidal, but it's halfway there. So just to sum up, the take-home message is that when you establish a poloidal Alfvén wave, which you can do through wave particle resonant interactions, that poloidal alpha wave can then evolve, and it'll do two things. It'll rotate its polarization, which it does in a box model, but importantly in a dipole, it's going to cross L shells. Once these, why is all this interesting? Well, aside from just the theoretical perspective, if you want to understand satellite data of particles, they will be influenced by these poloidal alphane waves and their rotated counterparts. There are observations showing how these sort of waves can modulate particle fluxes and energies. And I think we've got a talk after lunch where it looks like the effect of these sort of waves, ULF waves, on radial diffusion of radiation belt particles is also discussed. So it's important, if you want to interact with particles or understand how these waves affect them, is to understand what field line is the alphane wave on, and also what is its polarization, because the key way that the wave is going to affect particles is through its electric field. Now, the electric field is going to be perpendicular to this MHD velocity. So it starts off with a toroidal field, and then it rotates here. It's inclined midway between toroidal and poloidal. And that electric field, say, it's how it's going to determine the effectiveness with which the wave influences particles. Okay, so I'll finish up there. Thanks for your attention.
Thanks, Andy. That was great, and thanks for the intro. Was great as well. It was a very nice way to see phase mixing. Was fantastic. Claire, how are we doing? Have we got anything in the Q&A?
People have been really quiet on the Q&A and the chat for this particular session. I'm inviting people to throw a quick question in, or indeed just indicate that they've got a question. We could let you ask it in person.
That's true as well. Any takers? I realize it's we've got Mark.
Mark's got one. Hang on.
Right, I can, or you can do that. You've got that.
Yeah.
Hi, can you hear me?
Yeah.
Yeah, great stuff, Andy. I was just wondering if there's also an effect on the compressional component of the magnetic field during this phase mixing, and what that might have implications on particles as well.
Yeah, thanks, Martin. Well, there is actually a compressional field in this wave, but it's very small. If we go back to this requirement for the poloidal wave, if I say this is much less than 1, let's call this epsilon, this ratio, you actually get a compressional field, but it's of order epsilon squared. So it is small, it's there. It's probably not going to be the dominant thing affecting the particles, though, because it's small. I did invite you to think about how can this alphane wave start on this field line here and finish up on this one. And the way it does it is actually through that very small compressional field. And it's that small pressure gradient which basically keeps establishing newly resonant responses on neighboring field lines, but with slightly different polarizations so that the frequencies are all matched with the original one. So that compressional field is important for this sort of evolution, but I wouldn't have expected it to be that important for affecting particles.
Great. We've got another question from the Q&A from Q Stanley. Do the oscillations continue to rotate, or does it rotate back? And it's good that you're on this slide, I guess. Yes.
Yeah, it's an irreversible rotation. It will just keep going and asymptote to being completely toroidal. If you actually think about starting with a toroidal alphane wave, so you basically need to rotate this diagram through 90 degrees so that the ridges are aligned up in the radial direction, that would phase mix. It would build up smaller and smaller scales in the x direction, but it would stay as toroidal. So there is something different about the toroidal wave to the poloidal. The poloidal wave phase mixes and brings about its own downfall. The toroidal wave won't.
Great, thanks. I think that's all.
Okay, thank you.
The questions there, Tom.
Okay, thanks, Claire. And thanks, everyone. Sorry for running on. I find it hard to tell my old PhD supervisor to be quiet. So, but no, thanks, Andy. That was great. So we're going to be back at 1:20. Sorry for the short lunch break. It's packing a lot of talks into one day. I do apologize for that. Hopefully it's time enough for everyone to grab a quick bite. So we're back here at 1:20 for the next set of talks. Could the speakers for the next section just turn up 5 minutes before that, so maybe at 1:15 or so, and we'll get you onto the panel and check the screen sharing is working okay. Otherwise, everyone enjoy your lunch. Thanks for the great session. Thanks for the speakers, and I'll see you in about half an hour or so. Okay, everyone, so I make that 20 past. Sorry for the short lunch break. Hope everyone grab something to eat quickly and are energized for our next session. So without further ado, we'll get started right away with our next speaker, who is Theodoros Saros. So if you could please share your screen. And he's going to be talking about flux oscillations in ULF range of frequencies as indicators for radial transport processes. So please take it away.
Great. Yes. Hello, and great to see everybody. So as the title says, in this talk, we'll explore a new way to probe the magnetosphere and the radial transport processes therein via flux oscillations. And the main idea came out of back in '74 from the Schultz and Lanzarote book on radial diffusion, who applied it for general radial transport processes. And here we'll show some simulations and observations of such flux oscillations. So an example was observed, or a series of examples were observed during a prolonged quiet time where gradual radial diffusion was observed. And this is during the quiet time of approximately 11 days between the high-speed stream on March 1st and March 17th. And during this very quiet time, we're able to see oscillations at hundreds kilo electron volt electrons, and these flux oscillations are at the drift frequency of most energy channels during that time. This is during one pass from the Van Allen probes measured by the MAGAIS instrument. And such oscillations are observed over and over consecutive orbits, as we can see here. So these flux oscillations occur very often. We also did a statistical study of these events, and in the past, such oscillations have been associated with storm events and substorm events, and they are called drift echoes. Herein, however, we'll show that these oscillations are associated also with ULF wave-driven radial diffusive processes, and that they contain information that could be used in determining or assisting to determine radial diffusion rates. So the underlying process of these resonant interactions of an electron with an ultra-low frequency wave of the similar frequency, similar to its drift frequency, is shown in this plot, where for an m equals 1 azimuthal mode number in the left, and the resonant interaction with an m equals 2 mode number wave and of twice the drift frequency is shown in the right-hand side. And then looking at the resonant interaction of the same waves with a ring of electrons, as shown here, we can see that some electrons are in phase, in resonance with the wave, and they're transported inwards, gaining energy, and they're color-coded red, conserving the first adiabatic invariant, and others are out of phase and are transported outwards, losing energy, and energy is color-coded here. The blue ones lose energy, and the same happens for an m equals 2 mode number, as shown in the right-hand side panels. And these are resonant interactions with monochromatic waves. So in a simulation, we then included broadband waves of the entire range of relevant frequencies, and we investigated the effect of these broadband waves onto a particle population in the inner magnetosphere. So the analytic forms of the azimuthal electric field and the consistent magnetic field are given in this term, and they're consistent through Faraday's law. And the power spectra during this time, the measurements versus model is shown in this plot, just to show that we are in the same order of magnitude of ULF wave power during this time. So we conducted a particle tracing simulation, and we've added energy weighting to all the particles in the simulation, and this is the power law, the energy spectrum that we used. It's actually 2 power laws, and the the energy weighting was done so that according to the energy spectra, the measured energy spectra during this time, and we can see. And we also introduced distribution in L to the electrons in the simulation. So we can see that the particle tracing simulations reproduce reasonably well the resonant flux oscillations during this time, with oscillating fluxes at each of the energy channel drift frequency ranges. So we went on to investigate the parameters that are mostly affecting these oscillations. And one of the key parameters is the energy channel widths of the energy of the channels measuring these flux oscillations. So in a simulation, we artificially change the energy channel width, so shown in this in the horizontal axis. We introduced in the simulation different energy channel widths, and we measured the resulting flux oscillation amplitudes during this time. And the results are plotted in these curves for the various energy channels. So what we can see is that wider energy channels lead to lower observed flux oscillations. And we then went on to introduce the actual energy channel widths as the Van Allen probe's MAGAI's instrument have. And these are shown in the lower right panel. So the energy channel widths as a function of energy, and MAGAI's has a low part of the instrument of the energy spectrometer, and a medium range of energies for the spectrometer, with distinct energy channels for the different parts of the instrument. So if we introduce the actual energy channels in the simulation, we can predict the expected flux oscillations for the given electric and magnetic field fluctuations that were introduced in the simulation, and which match the actual spectra of electric and magnetic field, the ULF wave power. The resulting flux oscillations are shown in the colored, the simulated flux oscillations, the expected flux oscillations are shown in these dots, and the actual flux oscillations during these times are shown in the colored dots. So we can see that the actual flux oscillations slightly exceed those predicted in the simulation, at least for the lower energy channels. And these discrepancies could be due to additional electric and magnetic field fluctuations that could be experienced by the electrons elsewhere along their drift path, away from the region along their drift path that the measurements are made. The width of the energy channel spectrometers of the spectrometers is a key parameter that enables the observation of these flux oscillations. And the Van Allen probes currently have one of the highest energy resolutions. But as we show here, perhaps it's still not high enough for higher energy channels. Even though latest studies also with a REPT on the Van Allen probes shows that flux oscillations are observed in even in the MEV electron channels. We then went on to investigate another parameter that also affects the energy channel, also affects the flux oscillations together with the energy channel widths. And this is the local phase space density. So for this same event, we plot here phase space density as a function of L star. And we can see that there is a variable phase space density that's observed around the Van Allen probe's apogee. So the apogee is shown here within the red box. And phase space density gradients range from positive radially outwards to 0 for the yellow energy channels and to negative for higher mu values corresponding to higher energies at the Van Allen probe's apogee. So in the corresponding area in the area on the left-hand side, we see the gradients with 0, close to 0 phase space density gradient for the yellow channels, and the corresponding channel or the corresponding energy channel of the Van Allen probe's MAGEYES instrument shows 0 or close to 0 flux oscillations. So non-zero gradients enable the observation of higher amplitude flux oscillations, and larger gradients lead to larger flux oscillations. So phase space density is a key parameter enabling the observations of these oscillations.
Yep, your own conclusion. Sorry, about 1 minute.
Super. These simulations and these observations show that there's information in the amplitude of oscillations of electron fluxes, and they contain information of the ongoing radial transport processes. And these observations are enabled by the very high energy resolution of the Van Allen probes. Overall, the flux oscillation amplitudes will depend, as we have shown, on the width of the energy channels, the gradients of phase space density, and of course also the amplitude of electric field oscillations, which is also introduced in the simulation. And as a second slide of conclusions, this association between radial transport, flux oscillations, and phase space density gradients, as well as the power of ULF field oscillations, could lead to an empirical relationship for a radial transport coefficient. And the question here is, why would we need another radial transport rate or a diffusion coefficient? And the key point here is that diffusion rates as currently calculated depend on measurements of electric and magnetic field fluctuations, which rely on having satellites at the place and time where these diffusive processes occur. Which is not always possible, whereas electron flux oscillations carry the formation everywhere along the anywhere along the electron drift paths, and so this information is available even at the regions where field fluctuations, beyond the regions where field fluctuations occur or are observed. So they can be used to probe the inner magnetosphere even at regions where there's no measurements, and this is something that we're currently working on. Thank you very much.
Okay, thanks very much for that really nice talk. Do we have any questions, Matt?
None that I can see currently in the Q&A or in the chat. I did have a very simple question, though, if you don't mind. So you said that the being able to see these oscillations in the fluxes depends very much on the width of the energy channels. Why is that?
So if we can take it to the extremes, an infinitely narrow energy channel would essentially measure only one energy, and this would be a particle drifting around the Earth, creating a pulse, and then an infinitely wide energy detector would include phase mixing of all different drift velocities and energies of different particles. So they would all phase mix, and you wouldn't see these flux oscillations. So there's yeah, the narrower the width, the more the better that these oscillations can be identified.
Thank you. I had a feeling it was probably something along those lines, but obviously I didn't know for sure. We've not got any more questions as far as I can tell. So
okay.
Yeah.
Yeah, I mean, we are in the unique situation here where our speaker is around for a little bit longer. So if you do have any questions about this talk, then please drop them in the Q&A, and we'll have a chance to potentially answer them after the next talk as well. So I'm just going to let you carry on with a discussion on the distribution of ULF wave power in magnetic latitude in the inner magnetosphere. So if you'd like to just load up the next one, that would be great. And I presume there will be more questions as well. I definitely know there's people in the audience who will be interested in this kind of stuff. So, so do get those questions in. Right,
and sorry to carry over. I wasn't sure which subject to present today. This is something that we've been working recently, and these are fresh results. And I appreciate everybody's feedback on that. So it concerns the distribution of ULF wave power in magnetic latitude. And this is my list of collaborators in this work from the Democritus University of Thrace and LASP at the University of Colorado, as well as the Themis and Arace teams. So this the study of the distribution of ULF waves in magnetic latitude is enabled by the inclinations of the Themis and Arace spacecraft. And Themis has an inclination of about 11 degrees, whereas Arace has an inclination of about 31 degrees, and the L shell or the apogee is not shown to scale here. And they span very different ranges in L. And together with the tilt of the magnetic axis, this enables obtaining a range of magnetic latitudes away from the equatorial plane. Which is currently it's one of the main sources of in situ measurements of magnetic fields. So if we put these together, this plot shows the total observation time as a function of L and magnetic latitude for Arace with an inclination of 31 degrees. So plus 11 degrees of the dipole tilt, that goes up to 42 degrees, even though the last range of bins here doesn't have sufficient observation time and is not included. And similarly, Themis enables the observation of magnetic latitudes up to approximately 22 and a half degrees. So we've put together all 14.5 years of Themis measurements from Themis A probe and 3.5 years of ARASE or ERG satellite measurements. And we plotted the magnetic field in field-aligned coordinates in the parallel, azimuthal, and radial components, and we calculated the total ULF wave power in the PC4 and PC5 range of frequencies. And this is what we get. These are the ULF wave spectra in the three components in the field-aligned coordinate system as a function of L and magnetic latitude. And you will note here a region that's marked with a magenta color. And these are the regions where the spacecraft velocities are rather high for the ARASE spacecraft. So in order to avoid Doppler shift effects, as we heard earlier in earlier talks, we do not consider these ranges. So the innermost or the regions closer to perigee. So what we can see here is firstly, that there's a minimum in ULF wave power at or close to the magnetic equator for all three components, for the parallel, the radial, and the azimuthal components. Second point is that the radial component appears to have the largest power away from the magnetic equator, followed by the azimuthal component, and then by the parallel or the compressional component. So from these observations, and also that the radial and the azimuthal component appear to have a deeper minimum at close to the magnetic equator than the parallel component. So comparing this with the natural modes of oscillations in the ULF range in the magnetosphere, we can see that also toroidal pulsations would have, according to theory, they would have a node for azimuthal oscillations in the azimuthal component. And this appears to be the lowest amplitudes. Similarly, the radial component would have a node or zero amplitude fluctuations, whereas the parallel component would have a minimum but finite amplitude, at least according to these models. Also, comparing these modes of oscillation with the statistical analysis, we see that the amplitude increases asymptotically for the toroidal pulsations and azimuthal fluctuations shown here at higher latitudes, whereas for the radial component, this increases exponentially, and the radial component shows the largest amplitude of field oscillations, whereas the parallel component will have finite oscillations at higher amplitudes. We've also conducted a similar study for the electric field oscillations. This is still ongoing, and the electric fields show a maximum close to the equatorial plane, as also is expected from theory for the azimuthal electric field corresponding to the radial oscillations. So The implications of that are a few. First of all, ULF waves are known to radially diffuse hundreds keV to few MeV electrons in the magnetosphere, and diffusion coefficients are mostly described by analytic expressions for radial diffusion coefficients that are derived primarily for equatorially mirroring electrons, so close to the equatorial plane. And similarly, the analytic expressions that estimate diffusion coefficients and diffusion rates are based on measurements of the power of ULF waves that are made from spacecraft close to the equatorial plane, or averaged across all latitudes, or from the ground, and ground measurements are also sometimes limited in the way they observe ULF waves. Another implication from these 2 points is there's commonly or it's in some studies it has been concluded that the magnetic diffusion coefficient or the electromagnetic part of the diffusion coefficients is considered to be an order of magnitude lower than the corresponding electrostatic diffusion coefficient. These statistical observations show that this might be due to a lack of measurements at up to now at higher latitudes. These diffusion coefficients primarily concern equatorially mirroring electrons. And these measurements show that wave power increases away from the magnetic equator, and this could have implications for radial diffusion rates as currently estimated. And this points to the need for pitch angle dependent diffusion coefficients. And I'll leave this open for questions. Thank you.
Thank you.
So we have a question in the chat from Jasmine. So really interesting to see that the statistical analysis shows power increases away from the equator. Are there any conjunctions of Arase and Themis to see this on a case study basis?
Yes, there are conjunctions that enable us to compare the amplitudes of across the two spacecraft. I would say that the cross-comparing the fluctuations in the magnetic field is less prone to discrepancies between the instruments, as is common with electron spectrometers, because flux oscillations, field oscillations. In field oscillations, we are not so much interested in the accurate cross calibration between the magnetometers, for example, and also there. It's more, it's easier to cross calibrate magnetometers than it is to do, for example, for electron spectrometers. Yeah, there are times where the spacecraft are close by, and we have done such comparisons. But this is this statistical study is done for the whole precessing orbits of Themis and Arase. So there's precession both in latitude and also in local time.
Brilliant. We have another question also from Jasmine. What MLT sectors does the statistical analysis correspond to? Do you expect the statistical results to vary with MLT?
Right. So during this time, so over the 14 years of Themis data, the spacecraft processes 3 times overall local time sectors. And for the Arase time, over the 3.5 years, the spacecraft processes twice or around all local times. And we've actually cut the time periods that we use so that there is the number of precessions in overall local times is a round number, so that there's no biases. But we would certainly like to expand this statistical analysis to see these dependencies over different local time sectors, because there's different factors affecting the flux oscillations on the day side, on the night side, with fluctuations in the tail or on the flanks, and these would be very interesting. Also, as a function of KP or geomagnetic activity, we would like to see how this varies. So this is all the statistics, and now we can sector it or break it into more refined analysis.
Brilliant, thank you for that.
Okay, I think if that's everything, if there's any other questions, please do put them into the Q&A or into the chat. But otherwise, thanks very much for your nice presentations.
Thank you.
That's really great. And I'll ask us to move on to Andy. So if you could, stop screen sharing, please. Thank you. And Andy, if you would like to share your screen. So our next speaker is Andy Smith. He's going to be talking about magnetosphere-ionosphere coupling at substorm onset through ULF waves. So Andy, just when you're ready, take it away.
Hello. Hopefully, there we go. Hopefully you guys can see my screen. I'd like to thank the organisers for putting together this conference. It's been great so far. And today I'll be talking about magnetosphere-ionosphere coupling at substorm onset. And there'll be ULF waves involved in that. So if you were to take a picture of the aurora from above the North Pole during substorm onset, you might see a progression of images such as this. So in the top left, we can see what's the more quiescent auroral oval. So midnight is off to the left here and the sun is off to the right. And we see a series of images over about 10 to 15 minutes. And the end result is we see the bright auroral arc forming during substorms. But if we actually go in more detail, particularly at the midnight arc, what we can see is some structure forming just before the brightening. So there's this azimuthal periodic structure known as auroral beads. And that brightens throughout the arc. And then everything starts to kick off by about the second panel down. So the question that we have is what's causing these, what phenomena is related to it. If we were to look at these from the ground, so instead of looking from space, we're looking up from the ground. These are all sky images, and we have a similar progression here. We have the auroral arc here, and as we progress through time, we start to see this periodic structure emerge. What we can do is we can take a slice through that arc and see how it changes over time. And that's what's plotted in the second panel down here, where we have a keogram, so the brightness as a function of longitude and time. And we start to see this periodic structure appear as these diagonal stripes here in the brightness. If we take vertical slices through this and perform Fourier analysis, we can extract the dominant wave numbers. So in this case, the dominant wave number here is about 1 × 10⁻⁴ meters. If you were to do this kind of analysis statistically, as Calmonier did in 2017, you'll find that this can account for roughly 90% of the auroral arcs that you see at substorm onset. So this structuring is quite common to substorms. And the question then is, does this structure tell us something about the processes that are active during substorm onset? If you were to have a magnetometer below those beads as they're forming, what you'll find is that they're associated with ULF wave growth. So on the left-hand side here, we have a study where we're looking at PI waves. So in the probably seconds to hundreds of seconds kind of periods. And around auroral onset, this is a statistical study with a superposed epoch analysis approach. You'll see an exponential increase in ULF wave power in these kind of period bands. And that's roughly what's co-located with substorm onset. And the timing is very similar to the time that the aurora brightens. If you are to take a ULF wave onset time, so often in this kind of study it's taken as when your ULF wave power rises to 2 sigma above the mean of the quiet time, you can actually plot out this a delay map of when ULF waves arrive at a certain station. And that's what we show here on the right. So we have a series of stations here over Canada. The color of the contours here shows the time that the ULF wave power rises above 2 sigma above the mean. So for example, here in this contour here, we have 60 seconds after the first sighting. Then we have about 2 minutes, it's expanded this far, and then about 3 minutes, it's expanded even further. If you are then to plot where you would say that the auroral onset started, you get this red cross here. So you find that they're pretty much co-located. So at auroral onset, we have the development of the large-scale current systems. We have the auroral onset, the auroral brightening. We have the beads, and we also have ULF waves, all pretty much co-located in space. So this has been suggested to be the ground signature of a growing instability in near-Earth space, roughly in the region where we transfer from a dipolar field to more of a tail-like structure. So we have all this observational evidence on the ground, but what can we see of the conjugate processes? So to do that, what we need is we need a substorm onset, all-sky images that can show us beads, ground magnetometers that can show us the waves, and then we can examine the conditions in near-Earth space. So here we have an example of that. So the top panels, we have a series of all-sky images with the auroral arc up here in the top right. And we can see that as we go through time, we see this kind of periodic structure develop in the auroral arc. If we look at a keyogram of that, we can see that that's kind of, well, the times of the images are given by the blue vertical lines. And throughout this time, we see that the aurora is moving poleward. We also see that the brightness in the aurora is increasing exponentially, as we'd expect at substorm onset. And at the co-located magnetometer, if we look at the wave power in the horizontal field with periods of between 10 and 100 seconds, what we see is that the exponential increase in wave power is seen here at the same kind of time. During this event, we have 3 Themis spacecraft that are located conjugate in the tail, so around 10 Earth radii away from the planet. And we see exponential increases in the wave power that they observe, in this case in the perpendicular field, with periods of between 10 and 100 seconds. So it stands to reason that we're seeing the same kind of waves along the same field line. By eye, it looks like the waves start in space, and then we see them later on the ground, but it is just looking at this kind of plot by eye. So instead, what we can do is we can look at it statistically. So we took a tail season from Themis in 2009, and we found there were 150 intervals where we saw exponential increases in ULF wave power on the ground, and we also had the corresponding spacecraft measurements along the same field line, so roughly conjugate. Of those 150, about 100 showed correlations that were above 0.9. So we performed a simple cross correlation to look at the timing of that peak correlation. And when we did that, we found that the space observations led the ground by around 1.5 to 2 minutes. So we can interpret that as some kind of travel time of the broadband wave signatures to get from near-Earth space into the ground. So it basically confirms that we're seeing the result on the ground of this space-based process. If we want to examine the communication pathway in more detail, we can break it down by period frequency. I realize that most of the talks today have talked about in terms of frequency, so I'm going to flip it on its head a bit and talk about periods. So this is a different event where again we have all 3 Themis spacecraft in the near-Earth tail, and we have corresponding ground observations. The top panel here just shows a contextual panel showing the increase in perpendicular wave power of around 4 orders of magnitude here, just prior to the substorm onset time that you derive from things like the SML index. In the bottom 3 panels here, we have the 3 Themis spacecraft. This is the continuous wavelet transforms of the perpendicular field, and I'm showing power spectral density here. Because it's a wavelet method, there is some uncertainty in the timings associated with this, and we've illustrated this with the white dash line here. So we can see as we move from periods of around 10 seconds up to 100, the timing uncertainty increases as the wavelets become less exact, I guess. And what we can see is that there's a very strong increase in ULF wave power at all periods between 10 and 100 seconds. Accounting for the uncertainty, it's fairly simultaneous at all periods. And we also see that if we look at the colors here, the power spectral density at all periods is roughly equivalent as well. So we're not seeing a particular bias here, certainly in the 10 to 100 second period bands. Thank you, Kat. So we can do the same thing on the ground and then compare and contrast the results. So on the top left here, we have an example of the stations that we could use. So the black crosses here over the Canadian continent, or North American continent, show potential stations that we could have chosen. The ones that I'm going to show here are highlighted in the solid colored crosses. The footprints of the spacecraft are indicated with the circles here. I realize this is quite small. And the spacecraft are roughly co-located with Substorm onset. The following panels are for the ground magnetometer stations, where we show the continuous wavelet transforms. And as a rough rule of thumb, as we go down the panels, we get further away from Substorm onset. So what we can see here is, in contrast to the space-based observations, we can see that there's a bit of a slope developing here as we move away further from Substorm onset, indicating that the shorter periods, so as we move towards a period of 10 seconds, they become more delayed, certainly by the time we get to these kind of stations over here. What we also see is that the power spectral density is much more concentrated towards the longer period bands than in the shorter period bands. We can then plot these as maps, so we can look at the spreading of the waves away from this epicenter. So if we look at the longest period here, that we have a wavelet that corresponds to a period of around 66 seconds, we can see that the travel time to the ground is only around a minute, maybe, perhaps. And the waves spread quite rapidly, east and west and north and south. The spreading in longitude seems to be quicker than the spreading in latitude, but it fairly rapidly covers the entire continent. If we then look at the shortest period band in contrast, so this is about 16.5 seconds, we can see that the waves are much more confined, firstly in latitude, and secondly, the contours are much more closely arranged, indicating that they're spreading slower. The red crosses here indicate the spacecraft and Substorm onset. Something that could explain this is that the high frequency or shorter period waves are more heavily damped in the warm plasma sheet. So what we're seeing is the effect of the shorter periods being lower amplitude and taking longer to reach some kind of threshold that we're going to acknowledge as being a ULF wave onset. And this also corresponds to work that's been done using the auroral observations, where they Calmoni in 2018 evaluated an observational dispersion relation, and that was also consistent with the shear alpha waves. So just to summarize there, so we were looking for a repeatable signature of Substorm onset that could explain processes that are active in the near-Earth tail. We correlated ground and space observations to confirm that the source region of these waves is indeed in the tail. In terms of broadband time offset, we see a period of around 2 minutes, but we find that this period, this delay is heavily dependent upon the period of the waves. And this is likely due to the damping of the shear alpha waves by the warm plasma sheet. So the question is, what's generating these waves? I've conspicuously stayed clear of what that could be, but I see on the program that there's a talk by Jason later on that's looking at a process that could cause these at Substorm onset. And that's my talk. Thank you.
Thanks very much, Andy. I'll hand over to Matt to deal with the questions.
So we do have a question. Do you know what physical process initiates the waves in space before signatures being seen on the ground? In brackets, ballooning modes have been suggested previously.
Yeah, so there have been a number of different processes that have been suggested to cause this, but I don't think there's as yet been observational evidence in the tail from things like Themis to show that. I do know of some studies that have used global modeling to suggest that certain phenomena may be more likely, but I don't know if there's been observations of things like ballooning modes. I'm also slightly unclear as to how we would narrow down that it's a ballooning mode causing it. The data is quite messy, having looked at it.
There's another question as well. Have you looked at the average wavelength in kilometers and growth rate per second of those periodic structures detected in the magnetosphere/ionosphere?
Yes, there has been some really good work done by authors such as Calmoni and Ray, looking at the structure in the aurora and extracting wavelengths. Off the top of my head, I can't remember the kind of wavelengths we're talking about. It might have been about 150 kilometers, but I can't remember off the top of my head, if I'm honest. But if people are interested, I can point them towards references where they discuss that.
That's all the questions that appear to have at the moment. I do have a question, possibly two. You did. I think you might have mentioned it earlier on in the talk. What were the sort of azimuthal wave numbers like for the beads
Yeah, that's a good question. I'm not sure off the top of my head the exact wave numbers. Yeah.
The reason I asked was because if they are sort of, well, you might be able to see the signatures of these in the Substorm data potentially, if it's in the right place in the right time anyway.
Yeah, that's a very interesting avenue to explore. I don't know if that's been done.
No, I don't know.
Okay.
Wave numbers are 2 × 10 to the power of -4m. Is that m as in meters? What's that in terms of azimuthal wave numbers? I don't know. I'm not quick enough to figure that out in my head.
Yeah, he's clarified. He's getting his units right now, 1 over m. But okay, thanks very much, Andy. I might ask you a question in a minute, but otherwise I'm conscious of giving people a nice 15-minute break. So we're going to have a 15-minute break. We're going to be back at 2:20, where we'll hear from our friends across the pond. We've left our American speakers to the end. And that'll be the final block of this day of talks. So please rejoin us at 2:20, so in 15 minutes time, where we'll have our final 4 talks of the day. So thanks very much to the speakers in this session, and we'll catch you all in 15 minutes. I should also say to any of the speakers coming up in the next session, if you could just come back about 5 minutes before that, and we can test out the screen sharing, that would be great. Thanks. Also, Andy, if you are still there, Andy Smith.
Yep, I'm here.
First of all, I love the cat. Secondly, have you done any kind of sort of travel time analysis? So like, for instance, I know on the day side, sort of for like, kind of where you have say an impact, like a shock, an interplanetary shock, say impact, there's quite a lot of work being done on what's known as the Tamal path, which is basically working out the travel time of a wave based on if you have a compressional disturbance, which field line that kind of, where it propagates across field lines, where it hits a field line and then it propagates along the field line into the magnetosphere, and basically doing the kind of 2 components of that travel time. One as a compressional across field lines, and then one as your Alfvén wave along field lines. Do you know, could you do something similar in terms of like a travel time analysis for the waves you're seeing on the ground based on where you think they're initiated in space? And I don't know if that's because you showed a plot where things seem to be getting to, was I interpreting it correctly as in it was getting to different latitudes at different times, or that was at different periods at different times? I maybe misinterpreted.
Yeah, so you see the delay increase with latitude and also with longitude. We did a very basic form of that in the paper, where we looked at the travel time as a function of period. And we saw sort of the broad increase, so from 60 odd seconds for the longest periods through to 2 minutes or so for the longer ones. But we didn't go too much into the actual Tamal travel paths or anything like that. But certainly that'd be an interesting route to explore in the future. Okay,
yeah, because I guess if you've got it kind of goes back, I mean, Andy Wright he asked that first question, and it goes back to that, yeah, I guess that source, if you've got a common source location, then you should be able to track, which is, I guess, what, yeah, if you've got a common source location, you should be able to track how that then reaches. But I haven't really done any of that on the tail, so I don't really, that's, I guess you'd have quite weird shaped field lines, so that would be a bit of a difficult, it would be a bit difficult analytically because of your field, but I guess numerically that's probably not too bad.
Yeah, I think in the paper we discussed some of the travel times that we might expect for different paths, and just discussed that they were feasible, but we didn't go much beyond that into kind of decomposing it into like fast mode and then Alfvénic or anything like that.
Okay, cool. Well, thanks for the talk, much appreciated.
Thank you.
Cheers.
Yeah,
okay,
flexible. Okay, welcome back everyone. I'm Jasmine, I'm going to be chairing the next session. So first up we have very exciting to have an invited speaker, Shuni, to talk about geoelectric and geomagnetic fields driven by magnetospheric ULF waves. Would you like to start sharing your screen and then you can dive straight into your presentation?
Sure. So can you see my screen and can everyone hear me well?
Yes, perfect. Thank you.
Great. So hello, everyone. Thank you for having me. Yeah, I'm very excited to join this meeting with a focus on ultra low frequency waves, which is my research topic in the past 8 years since I was a PhD student. I also feel sorry that I had to miss most of the session, the talks before me, since it's a bit early for me. Right now it's 7 a.m. my time. So today I'd like to share my recent work on geoelectric and geomagnetic fields driven by magnetospheric ULF waves. First, I'd like to thank my collaborators for their contribution to this work, which was accepted in Space Weather Now. Here's the outline of my talk today. I will first introduce the link between ULF waves and geoelectric fields, and followed by the dataset and methodologies used in this study. Then I will introduce a few examples of intense geoelectric fields driven by ULF waves. Main results and findings will be summarized in the end. So here's the introduction. And the coupling between the solar wind and the Earth's magnetosphere and ionosphere generate varied phenomena that can drive geomagnetic perturbations. And the geomagnetic perturbations in turn can induce geoelectric fields within the conducting Earth. And in turn, this geoelectric field can drive electrical current that can flow in infrastructures such as transmission lines, power grids, and in the form of geomagnetically induced current, we call it GIC here. So ULF waves in the frequency range of a few millihertz to a few hertz, when propagating to the ground, they can couple to ground magnetic perturbations, geoelectric fields, and GICs. So the schematic on the right-hand side already shows the whole process I just mentioned. Just to note that for the geoelectric field, and it usually have a larger amplitude at the low conductivity regions, as shown by the longer vectors here, and have a smaller amplitude at the high conductivity region within the Earth. I believe my previous talk must cover lots of background material of ULF waves, so I'll talk more about the geoelectric fields here. So geoelectric fields are highly localized and depend on the Earth's conductivity, the frequency of ULF waves, and other perturbations as well. So they can be either measured directly or estimated using the equation below, where E and B are frequency-dependent geoelectric and geomagnetic fields, and Z is the surface impedance tensor, which depends on the Earth's conductivity. So the maps on the right shows the geoelectric fields derived using this equation with spatially uniform geomagnetic perturbations, a sinusoidal wave with different periods. And this map is in the upper Midwest of the United States, and here is Minnesota. So on the left, it shows the geoelectric field vectors color-coded by different, driven by different period of geomagnetic perturbations. Red is 10 second, 100 is black, the 100 second, and green, the 1000 second period waves. And on the right-hand side, the black vector are exactly the same with those showing on the left, which is a 100 second geoelectric field, and color-coded by the average apparent resistivity, which is a scalar and a proxy for this surface impedance, and it depends on the Earth's conductivity as well. And the blue dot shows a more resistive region, and the red dot shows more conductive regions. So two take-home messages here. One is that, as I mentioned before, geoelectric field depends on the frequency of the waves. As you can see, when the drivers have the same amplitude and uniform, especially uniform geomagnetic field, you can see like the shorter period with like 10-second ones, they usually have a larger geoelectric field compared with the longer period waves. And on the right-hand side shows, which I also mentioned before, like the more resistive region usually have larger geoelectric field compared with the conductive regions. So the previous case is just an idealized examples driven by spatial uniform geomagnetic perturbations. But we all know, like UF waves, they have like, because of different modes, they have different can have different spatial scales, spectral content, and wave period and amplitude. So it's still worthwhile investigating like the characteristics of geoelectric fields driven by real UF wave event. So more and more recent studies have shown that UF wave can be directly linked to geoelectric fields and GICs. One example shown on the right-hand side have a GIC maximum of about 120 N during a geomagnetic pulsation event at a 1 MHz frequency. However, this kind of direct measurement of geoelectric field and GICs are either very limited, or our community have limited access to those data because of various reasons. So it's still under debate, like if UF wave can drive significant geoelectric field, especially at the mid-latitude. So this study is motivated also by the lack of comparison from past work on the nominal geoelectric field amplitude driven by different sources, such as UF waves, substorm, and southern impulses. So in order to investigate the typical sources of intense geoelectric fields, including UF waves, so we use actual 1 second geoelectric field measurements from the Earth scope site, which is distributed across the United States. So these Earth scopes empty magnetotelluric sites are temporary. They measure the geoelectric field and the geomagnetic field for an approximately 3-week period, and then move to different locations, which results in a grid sampling of about 70 kilometers across the United States, as shown on the map on the right. So as I mentioned before, we want to investigate typical sources that drive these intense geoelectric fields. So the other data sets also include the Omni, solar wind data, geomagnetic indices. And in total, we found 16 geomagnetic storms with a DST minimum of less than -109 Tesla when the Earth scope geoelectric field data are available from 2006 to 2019. And on the right, it shows the list of the geomagnetic storm that we found and the available of Earth scope site. So it's been categorized into 2 classes. The first one is 6 storms with intense geoelectric fields being identified using the algorithm we will describe in the next slide. And there are 10 non-storm events, which we no intense geoelectric fields being identified using our algorithm. So we are mainly talk about the things being identified from these 6 storms and driven by UF waves. So here's the algorithm. So I will recommend you to refer you to the paper if you want to know more details. I just briefly introduced it here. Like this is idealized case, and this is when it applies to the actual geoelectric field time series. So we use a Python package which can find the peaks of a time series. So this is the sinusoidal waves. So you can find the peaks. In order to find both peaks and valleys, which is shown in the real event here, we make the time series the absolute values. And also we have some other criteria so that we can remove artifacts as those showing by the magenta star here, and keep as many physical events as possible. And one of the most important criteria we use that the peak needed to be topologically prominent above the surrounding signals by at least 500 millivolt per kilometers. So here's the method we use to identify intense geoelectric fields. And there I will show a few examples of events driven by UF waves. But before I do that, I'll just show you an example plot which we use to visually inspect, like if this is an actual event or artifact, and if to identify possible drivers associated with this intense geoelectric field. So this is the MF. data from Omni and the solar wind dynamic pressure, and the two horizontal components of geoelectric field and geomagnetic field measured by one Earth scope side, which we reported before, and then the AE indices and symmetric indices. So this storm occurred in 2011, October 24th to 25th. You can see two groups of events being identified. First one at the very beginning of the storm, it is associated with arrival epishock or storm sudden commencement. And the second one associated with the MF rotating and some variation in the solar wind dynamic pressures. We will zoom in more details then to analyze them. So this is the first event driven by epishocks. It's the same with the previous plot, but we zoom in centered around the epishock arrival. So you can see a very transient and intense geoelectric field being first peak we identified here, then followed by UF wave signatures, and the first peak of the UF wave being identified in the EX component. And you can also clearly see the wave signature in the geomagnetic perturbations as well. So yeah, this is an epishock-driven event. If you take a look at the left-hand side of the animation, the black line shows the geomagnetic perturbations, red line shows the geoelectric field perturbations. So in this case, since it's more of a global wave driven by epishock, so the black line are very uniform, similar with the synthetic case we introduced in the introduction part. And in this case, so it's more the Earth's conductivity is playing a role. I think only these two sides observe intense geoelectric field because it in a more resistive region. The other side, they all observe similar signatures, but similar geomagnetic field, but the geoelectric field is relatively small. So yeah, this is, okay, move too fast. So this is the second event, also the same storm, but from another Earth scope side, which is located here. And it's on the second day of that storm associated with a negative rotation of MF from negative BZ to positive BY. And also there's some dynamic pressure impulses as well. So the geoelectric, you can see very clear UF wave signatures, especially in the geoelectric field time series. You can see something in the magnetic field as well, but the magnetic field is dominated by a more larger scale magnetic perturbations. You can also see that from the left-hand animation. So in this case, I think both the magnetic perturbation, which is the black line, are not uniform and varies even from one side to another within these relatively small regions. So it's very localized geomagnetic perturbation as well as geoelectric perturbations. I think for the some of these can reach about 1 volt, but in this case, the wave signatures here, the amplitude is about 600 millivolt per kilometers. So this case elaborates the contribution of both Earth's conductivity as well as the source, that is the perturbation itself. And then this is a last example I will show about the intense geoelectric field driven by UF waves. And it is a relatively long period UF waves, as you can see from here. It's about 30 minutes. And I forgot to mention from the previous examples, usually like 1 to 2 minute period waves. And in this case, so the wave can sustain for a little bit of long time. So compared with the other mechanism and the two examples we showed before, this long period wave have a sustained peak geoelectric field, and thus may have a relatively stronger impact on infrastructures. So here's just put the UF wave driven geoelectric fields in the context with all the other possible sources we identified in this study. So definitely UF wave is one of the most common sources of intense geoelectric field during storms. And in some cases, which we showed in the last slide, the 2017 storm, it is the only source that drives the intense geoelectric field. And also each row here is for one storm. So the causes of the intense geoelectric field, it differs from one storm to another. And because it's dependent on multiple factors, which we mentioned before, and we elaborate more in the next slides, like the Earth's conductivity, the source, and the location of the observation relative to the source. So here, the map on the right, it shows all the about 200 Earth-scope sites we surveyed in 16 geomagnetic storms. And on the bottom, it shows only 24 sites, which actually observe the intense geoelectric field. To note that for this comparison, it includes all the drivers like UFO waves, IP shocks, and the substorm, etc. So as you can also see that like a few conclusions here, like most of the intense geoelectric field were observed at the resistive region, which shown as a blue dot here, and at a relatively high latitude if compared with all the coverage, because we do have more resistive region at a lower latitude, but these did not observe intense geoelectric field. So there are multiple factors that can affect if you observe geoelectric field at a certain location or not, like the local conductivities and what is the drivers, as well as the location of the observation as relative to the drivers. So here's a summary. I don't know how, if I have enough time to go through a summary, but I think I mentioned most of these points. So I just want to emphasize the last point that this is just the beginning of this work. So we are doing more detailed analysis to definitely need to analyze the drivers of each of those waves itself, which drive the intense geoelectric field, to investigate if there's characteristics of those geoelectric fields associated with different UFO wave modes. And also this is more or less of an interdisciplinary research. So definitely more collaborations needed between the MT and the power systems in order to characterize the drivers of the intense GSEs or geoelectric fields. And I think, that's all I have. Thank you for your attention, and I'd be happy to take any questions you may have.
Thank you very much. That was some really interesting results there. Tom, do we have any questions that have come through?
Yeah, we do. We have a couple actually. So from Andy Smith. So he says, great talk. Do you notice any effects where the resistivity changes across small spatial scales?
Yes, that's a very good question. I think so. So you can see from this side, right? I think there's certain boundary, because I only survey through this, there's actually the full coverage rather than North American regions. So in some, like in the Minnesota region, you see like at certain regions, this is more resistive, here is more conductive region. There's definitely a boundary there. And also because of, I think in the Northeast, there are also certain boundary caused by the Appalachian Mountains. So I'm not an expert on the geology, and that's mostly my USGS collaborators help me interpret that. But there's definitely in some regions there would be such kind of a uniform distributed Earth conductivity there. And this is also frequency dependent, so I only show one period. So if you take a look at other frequency or period, it would be different as well.
Okay, thanks for that. There's one more question from Jason Durr. It's just out of curiosity, why does the magnetotelluric survey lack coverage in the southern United States?
They're working on it. It's just that I think you mean this part, right? Yeah, this is tier 2019 where I'm studying this work. I believe they are still working on that to fill the gaps. So it's just a time issue. And also because of probably due to the pandemic, they do not have time to fill those gaps in the past 2 or 3 years.
And if I could just ask one really quickly as well. So you mentioned at the end that you hadn't really looked at the sources, or should I say, the specific ULF waves which are driving these events.
Mm-hmm.
Do you expect that to get this on the ground, you're going to need something like field line resonance to give you strong enough, or would that give you strong enough perturbations on the ground, or is this associated mostly with kind of substorm activity?
Yeah, that's a very good question. Probably need a further investigation, but I think some of the signature, like these ones and these ones, their wave periods are comparable to the eigen frequency at this local time, about 1 to 2 minutes. So there may be field line resonance, just that I haven't got time to analyze. And sometimes there would be a good opportunity. You have multiple chains here. I did find some field line resonance during some non-storm time. But yeah, you're right. It's either they're not at the right location, which more resistive regions, so not being able to generate a more intense geoelectric field, or it's the driver is not strong enough. But I do believe there would be cases the field residence will drive strong, intense geoelectric field when it's at the right location, and also at the relative to the sources. That depends on the if the source is strong enough or not, things like that.
Okay, great. Thanks very much. Jasmine, over to you.
Thank you. Yeah, let's move on to the next one. That was really interesting. If there are any further questions, feel free to use the chat or stick around. We'll keep the Zoom call running after the meeting. But yes, let's move on to the next speaker. We've got Jason Dow. Do you want to get your slides up and running?
Yes, thank you.
So yes, we've got Jason, who's going to be talking about the stability analysis of interchange stable plasma. Oh, 1 second, sorry, my screen moved. Plasma sheet to E cross B shear flow at substorm onset. Take it away, Jason.
All right, thank you so much. Yeah, so I'd like to thank the organizers for the opportunity to speak here. And of course, I'd like to thank all of my collaborators listed here, all from Rice University. And yeah, so as Jasmine said, I'm going to be discussing the stability of the plasma sheet, which is ordinarily interchange stable in most regions prior to substorm onset. And our group thinks that E cross B shear flow, as for example, might be seen at the sides of BBFs or bubbles or whatever your group calls them, may get sufficiently strong to destabilize the interchange stable plasma sheet. So that's the hypothesis. And I should mention, just because Andy Smith, one of his questioners, brought up something about ballooning modes. I should say there's a strong relation between interchange modes and ballooning modes. And I'm also working with my collaborator, Dr. Toffoletto and Dr. Wolf, on a project related to sort of figuring out what all the differences are between those two. All right, so as I'm sure most people are aware and has probably been discussed in other talks, although I was unable to attend all of them, auroral beads are a fairly pervasive signature of substorm onset, and they tend to show up in the ionosphere a few minutes after ULF waves show up in the magnetotail. And Dr. Nadine Calmoni did a statistical and optical analysis that resulted in empirical dispersion relations and growth rates as a function of wave number, which can serve as something to compare to for theorists like myself coming up with some sort of candidate instability to explain substorm onset. So the idea, as I said, is to use the bead structure to indirectly determine which ULF waves initiate substorm onset by comparing the growth rates and dispersion relations. All right, and so the growth rates peak around 0.045 Hertz, and the longitudinal wave number in the ionosphere is about 2 × 10⁻⁴ meters. You can see some other geometric features here. This image, by the way, was taken by a citizen scientist named Alan Duffy. I should give credit for that because I really enjoy this picture. Okay, so the model that we came up with, basically I took an older model of Dr. Wolf's from, I think, a 2015 publication, which developed a simple wedge model of the magnetosphere, and I supplemented it by including shear flow, and then did some perturbation theory. So this down here is basically the model. Since near the Earth, the curvature becomes, well, you get more dipolar region. The idea is that this can be approximately, this can be approximated by concentric circle field lines. You might ask why concentric circles. The idea is just to get something that's very analytically tractable and where the deviations from the realistic scenario aren't sufficiently bad that you would get order of magnitude differences in your frequencies and growth rates. So yeah, I mean, this is meant to be near Earth, night side of the magnetosphere. The center's taken, the center is taken to be the origin of a cylindrical coordinate system. You can kind of shift this around in the magnetotail wherever you want, and it should still work as long as it's within the nearly dipolar region. As I said, field lines are concentric circles, and it's just a simple model where all of the background fields vary radially. So that includes, I mean, the two most important phenomenological parameters here are the entropy, which governs the adiabatic pressure dynamics for the flux tubes, and the pressure, the velocity. Pressure and magnetic field are related to the entropy. So really, the velocity and the entropy are the two main phenomenological things to focus on here. We assume zero conductance in the ionosphere, and the whole system's taken to be an equilibrium pressure balance, and then we just perturb it slightly. I just took the MHD equations with an adiabatic closure, did some perturbation theory with normal modes that are dawn to dusk waves. These are frequently seen. And then I just combined all of the equations. This step here actually took a substantial amount of work that I'm hiding under one sentence, but I was able to combine them to get a completely decoupled equation for just one of the perturbed quantities. And then I took the low frequency limit to obtain the governing instability equation for the linear stage. And I end up with something like this after a couple different transformations, Schrodinger transformation among them. And I get something that looks like a wave equation with this effective potential here. Very complicated. But the two terms that play the most important role, and I'll be able to demonstrate that in my next slide, are the entropy term here. This is like a buoyancy frequency where the buoyancy is supplied by magnetic curvature. And then this is your standard shear flow Kelvin-Helmholtz term. Okay, so it took a while to realize that this could be rewritten in a more illuminating way. So basically you can see that I rewrote this in a series with prefactors that have Doppler resonances. And the reason this is important is because the resonances are going to dominate a lot of the behavior of the instability. And in order to end up with eigenfunctions and eigenvalues, which I don't yet have, you need a very, very fine array to resolve the resonances. So you need to figure out where they are, and then get your code to chop things very finely in the vicinity of those. So all of this is fine, but it's not very illuminating, because when you look at an equation like this, it's unclear what all is going on with all of this crazy stuff. I mean, these are a lot of terms. But once you read it like this, you realize that, okay, since the resonances are going to dominate most of the behavior, you can mostly ignore all this stuff at the end here, not the ky squared, but the other two terms. These V0 and V1 are hiding a lot of this stuff. Okay, and if you write it in terms of only the first two, which are going to dominate near resonance, you really get a Taylor-Goldstein equation, which is kind of nice because this is a well-known solved equation. I've been unable to solve it numerically, but I'm sure that's just me. So yeah, I mean, this is nice because all of these things, for example, this W here, we now have a Richardson's number. That gives us an instability criterion. We know that when the Richardson's number dips below a fourth somewhere in the domain, that's a necessary condition for instability. Now, it doesn't guarantee it, but it's helpful to know kind of where to look. And for those who are better with fluid mechanics here, the idea is that sufficiently strong stratification always has a stabilizing effect. So you need the W to go below that in order to destabilize the plasma sheet. Okay, and as I said, I don't have eigenfunctions and eigenvalues yet. That was the hope, but These resonances are really difficult to resolve sometimes. But the idea is that once I get them, I should be able to get dispersion relation and growth rates to compare to these two plots from Dr. Calmoni's 2018 paper for the empirical relations that she determined. And I should just mention as a side note, it is very difficult to know where this instability occurs. Of course, it's different every time. Satellite coverage isn't great. And projections are kind of difficult to do because you have to choose a field line model, and it's not really clear ever that your field line model is appropriate for the conditions that actually triggered the substorm. But the idea is that you should be able to map back and forth between the magnetosphere and ionosphere and at least get rough bounds on locations. And that's all I have. So thank you all for listening.
Thank you very much. Those some really nice equations there. Do we have any questions?
I don't think we have anything in Q&A just now. Let me just check the chat. We don't have anything in the chat just now. I could potentially ask a very naive question to begin with, unless. Oh wait, no, we do have a question now. I'll hand it over to so Claire Watt, who asks, does this model rely upon the presence of a BBF?
It doesn't. It only technically relies on the presence of shear flow for an interchange stable plasma sheet. Actually, it could even be interchange unstable. It's just that because the plasma sheet's so pervasively stable prior to substorm onset to interchange modes, yeah, that's just one particular hypothesis we're considering, because I think there's some evidence that the BBFs tend to be injections of energetic particles shortly prior to substorm onset. But no, you're right. I mean, strictly speaking, all we need is a background model that can supply each of these background fields as a function of radius. And then the only other condition is that the Richardson's number needs to dip below a fourth somewhere in the domain. So those are the only two strict assumptions that are needed. Okay, cool. She says thanks. I guess we have time, Jasmine, for another quick question.
Yeah.
If that's okay. So I guess I'm just wondering. So you showed the nice picture. I mean, this is just going to show my lack of knowledge about substorms and auroral beads in general. So please forgive me. So basically, you have some instability, and then is it that instability which drives the waves, which drives the auroral emission? Is that basically the sort of the process which is going on? Yeah, so I'm not, I think Andy Smith might probably have more illuminating things to say on that. I focus on the ULF wave that triggers the whole thing. But once the plasma sheet's unstable and you get this injection, it's unclear to me what the communication mechanism is between the plasma sheet and the ionosphere. My guess is it's kinetic alphane waves. At least that seems to be one of the best plausible explanations. But yeah, I'm not sure. I don't think anyone really knows. Okay, good. That makes me feel slightly better about the question. Cool. But thanks very much. Nice talk.
Thank you. Great. Thank you very much, Jason. So we're running to time. So let's move on to the next talk by Li Zhen. Would you like to get your slides up, please?
Hi, I'm Li Zhen Chen, research astrophysicist from NASA Goddard Space Flight Center. I would like to thank all the organizers and all the attendees. This is such a great opportunity to learn from different perspectives. Now I'll share my screen.
Great, I'll introduce you properly as well. So we've got Li Zhen, who's going to be talking about solitary magnetic structures developed from ULF waves, gyroresonant with solar wind ions at Mars and Earth. So over to you. If you can get your... Are you okay sharing? We can't see your
Can-
slides yet. Are you?
Oh, can you
okay?
see the full screen? Oh, not yet.
No, we can't see
Okay.
that you're sharing anything.
Okay,
You
let's
started.
see.
Okay, perfect. Thank you. We can see everything now.
Great. So we're going to discuss solitary magnetic structures developed from a family of ULF waves, gyroresonant with solar wind ions. We're going to use measurements from Earth and Mars combined with simulations to learn about the physics of these structures and think about how they might impact the magnetospheres and ionospheres of planets. So let's think about how these waves are generated first. That just picture on a quiet day with a typical wind speed and a constant solar wind. The machinery of physics of ion-ion instability draws energy from the relative streaming between the incoming solar wind and the reflected ion population to give rise to these waves, and they evolve into large amplitude solitary structures. Lucille, in her excellent talk, gave a very nice introduction on this picture. Now, so these, let's see, can you see the next slide? Okay, I assume you can.
Yeah, we can see a slide with some 6 panels on the right of MMS data. Is that right?
Yes, great.
Yeah.
So the best way to grasp what happens is to picture ourselves as blue star surfers riding on the wave as it move in and crash toward the Earth. The wave magnetic field, top 4 panels, By and Bz, grows in amplitude and steepens. Bottom panel shows the ion phase space density as a function of Vx. Yeah, X is approximately the shock normal direction and also the background magnetic field direction. You can see that the most intense red band, that is the solar wind population at about minus 400 kilometers per second. That's being modulated and slowed down and thermalized as the wave developing into solitary structures. The size of these structures along the X direction is approximately 10 to 30 ion skin depth. One skin depth is about 100 kilometers. And the YZ extent of these structures are of order Earth radius. This according to previous cluster observations. The wave magnetic field reaches amplitude 20 to 50 nanotesla. This is the kind of strength of IMF that can drive major geomagnetic storms. Such as shown here, an example of a major geomagnetic storm. You can see the BZ, negative BZ is about minus 30 nanotesla. And the density, the red trace in the third panel reaches 20 per cc. Now, back to the MMS observation, it's a zoom out view to show many of these pulses. You can see the ion deceleration, thermalization, electron heating, and these magnetic field and density pulses. They are correlated. Their enhancement can reach, or typically it's about an order of magnitude compared to their upstream values. So they have amplitudes that's comparable to those that drive geomagnetic storms. The difference is that they are pulses of durations several seconds. Now, can atoms of these waves and structures impact the magnetosphere, and how? So this is the driving question. And we attempt to address this question with 3D global hybrid simulations. Here's an example where we have a quasi-radial IMF with a weak northward BZ component, just like the setup that Lucille used in her 2D Vlasov simulation. So with this northward IMF BZ, we do not expect to see magnetopause reconnection equatorward of the cusp. The reconnection that can occur under northward IMF is tailward of the cusp. But yet here, because of these Foreshock negative negative BZ that's generated locally upstream, not from the IMF, but generated by the ion interaction, produce these bursty magnetopause reconnection. Here's an example illustrated with, for example, the white field lines inside traced from the magenta circle are closed at T1, and they became open at T2 as the magnetopause moved into this magenta circle. And associated with this reconnection, you can also see magnetopause indent illustrated in the right panel in the 3D view. The size of the indent is of order several Earth radii. So that was for a planet with a strong magnetic shield like our Earth. You can see bursty magnetopause reconnection and indents. For a planet, a much smaller, well, a smaller planet, but with a much smaller magnetosphere, that like Mars has to rely on induced ionospheric current and crustal magnetic field to stand off the solar wind. That standoff distance is typically less than 30 ion skin depth. For Earth, the magnetopause standoff distance is 600 DI. So there you see the difference. And so for Earth, it's just bursty magnetopause reconnection and indents of several Earth radii, but for Mars, it can be a big deal. Now let's look at examples of Mars Foreshock magnetic structures. Top panel shows magnetic field pulses enhancement, and second panel shows 3 component. You can see those negative BZ bipolar pulses. And third panel, the ions energy spectrogram, you can see the solar wind population at 1 keV is being disrupted, thermalized, and decelerated. And fourth panel, electrons. You can see electron heating. That's even more dramatic than those occurred in the magnetosheath. That's around 1900 UT. Corresponding density enhancement. And the bottom panel shows the IMF that's quasi-radial. And it's really until you begin to have the IMF mainly along the X direction, you start to see this huge enhancement of the magnetic field. A little bit zoom in, and with this green orbit to illustrate the location. So you can see it's mainly at the Foreshock, and the wave activity suddenly stopped as soon as this spacecraft goes beyond the Foreshock region, like more north of the Mars, above in Mars coordinate Z, above about 1.2 Mars radius. To the right, the zoom in shows that these ions are primarily H+. And you can also see this, the bipolar pulses in all 3 components and the correlated magnetic field and density enhancement. Now we put together Mars measurement and Earth's side by side. Both show solar wind ion thermalized and reflected. The top panel for both left and right at 1 keV, that's the proton, the solar wind proton. The second panel is again the ion phase space density integrated over Vx and Vy and Vz and shown as a function of Vx. And you can see the solar wind population being disrupted, thermalized. The third panel shows electron heating. And you can see the BYZ pulses and density correlated density pulses. These waves are primarily right-hand polarized in a spacecraft frame for both planets. Now we compare the pulses with particle in cell simulation results. Both in the observation and simulation, you can see these transverse component By and Bz, and they develop into more solitary isolated pulses as the thermalization process go on. So for Mars, the data resolution is not sufficient for this ion distribution function comparison, but for MMS, you can look at in detail and really in high cadence to look at reflected ion, how the solar wind population is being reflected. As indicated with these magenta arrows, shows this arc-like structure that signifies the reflected solar wind population. Now we can look at Vx, Vy 2D velocity distribution functions from both planets and compare with the simulation as well. That's shown as the top right 3 panels, the incoming solar wind and the locally reflected solar wind. If we take the simulation interval, the region that just around this thermalized and reflected ion population and put it, zoom in as the lower right 3 panels, you can do particle tracing for just the solar wind ions to get a sense of the nature of the interaction between ions and the wave. So from an earlier time, T-2, the distribution is roughly solar wind-like at the location where you mark with a vertical magenta line. If you take that small spatial bin and take all of the ions, all of the solar wind ions, trace them forward in time, you get these magenta circles at time t. And you can see that a lot of these ions trace out the phase space structure, this arc structure, and some of them are accelerated both toward the sun and toward Earth. And if you do a histogram of these ions, you can get this density profile that is very similar to the net density profile. So that tells us that it's not a fluid type picture that can capture really the essence, but we do need to view the ions as fully kinetic. So here I compare the mode that resonant with solar wind ions and the mode resonant with beam ions. The prevailing picture is mostly that in the Mars environment, the prevailing mode is a 30-second low left-hand polarized magnetosonic mode. These are primarily due to interaction of incoming solar wind with newborn protons. And these newborn protons, you can see in the second panel to the right, that they have an average streaming velocity, slightly negative. So they are also moving away from the sun because of the pickup process. So that is the primary resonant mode. And you can see the BYZ pulses are typically unipolar, while for the mode that resonate with solar wind ions, they tend to be bipolar. So there is a difference that can lead to day-side reconnection with crustal magnetic field, for example.
Could you just move on to your summary slides now and wrap up, because we're coming to the end of your talk, if that's okay?
Yes, so this is basically a summary slide in a sense that look at this global picture of the ion escape. It's mainly night side. This is from the data, and this is a schematic, mainly night side. However, now we take into account this new mechanism that even under quiet solar wind conditions, Martian ions may escape to day side due to Foreshock turbulence bombardment. And these escape ions can further enhance the turbulence and hence open this day side escape channel. So that's a work in progress, and that's a new picture. Thank you.
Thank you very much. That was really interesting. If we have a super quick question, we can squeeze that in during the handover. Do we have anything, Tom?
There's nothing in the chat or the Q&A just now, but I would just suggest that, yeah, I mean, it's in 15 minutes time, we'll be sort of wrapping things up and we can ask some questions then as well. So if anyone does have any questions for the speaker, please don't hesitate to put them in the chat, and I'm sure we'll get them answered in 15 minutes or so.
Yes, we can come back to them. But let's move on now so we don't overrun too much. So next we have Simone. Could you get your slide up while I introduce your talk, please? Thank you. Great. So next, our final speaker of the day is Simone Di Matteo, who's talking about ULF magnetospheric waves in response to solar wind periodic density structures. Over to you.
Okay. Thank you very much for the opportunity to present, and thank you for organizing this meeting and discussion. I'm a research scholar at the Catholic University of America and NASA Goddard Space Flight Center. And this work, I would like to thank my collaborators. And for more details, this has been recently accepted for publication in JGR. I'm going to discuss ULF waves that are result in the magnetosphere due to the impact of periodic density structures. So first of all, what are these structures? They are fluctuations that occur in the solar wind density that range from a few minutes to a few hours. And in this figure, you can see an example that is also the case event that I'm going to discuss. So in the top panel, there is the proton density, and the vertical line identifies this enhancement in density that has a typical periodicity of 90 minutes. They usually occur on solar wind stream with an almost velocity, and their boundary usually are associated with strong variation and discontinuity in the magnetic field, as you can see here, especially in the first structure here, we can see this sharp variation. In the bottom panel instead, we have the thermal and the magnetic pressure that are in antiphase, and they result in an almost constant total pressure, indicating that these structures are in pressure balance. Typically, these periodicity are associated with the particular length scale that occur more often than other, and this was a result of an analysis done on the wind observation covering almost 2 solar cycles, and here in this panel is a summary cartoon. So on the x-axis, we have the frequencies and the length scale that are obtained based on the solar wind speed. And as you can see, there are some structures that has a length scale that are persistent, and others instead that show some solar wind solar cycle modulation. And these are important because if we consider then with respect to the Earth magnetosphere, they have length scale that are comparable to the entire scale of the magnetosphere. And what they can do is engulf the entire magnetosphere and drive a fluctuation at similar frequencies in what we usually refer as a forced breathing mode. So if we look at the typical periodicity of this density structure, they go from 0.2 to almost 4 million years, and they overlap with the range that we usually call the PC-Phi wave. So for this case event, we had the two GOES geostationary satellites that were located symmetrically around noon. And in this panel, there are in black the relative observation in the PEN component. And we compare them with the result of the Tsiganenko model, where we consider only the magnetopause current contribute or all the currents. And as you can see along the compressive component in the top row, we are able to reproduce the long-term variation, but also the small scale that were directly related to the fluctuation in the density, and in this case, were drive the magnetosphere through the dynamic pressure. On the other two components, instead, we can see fluctuation at similar time scales, and these are actually the PC5 ULF wave that happen at the same time. So to distinguish between the two contributes, we needed a robust spectral analysis procedure that we developed and was actually focused to distinguish waves at discrete frequencies in between in a frequency range below 5 milliards. So here is an example. There is the time series of the density of the solar wind, and we use the multi-taper method. So we use this method because provide the identification of the waves in two ways. One is what we call the gamma test. We basically evaluated the power spectral density on which we fit a model that can be a power law or a bending power law. And based on that, we can define a confidence threshold, and the peak above that are the one that we consider likely to represent periodicity. And the other test is an independent statistical test that is called the F test, that check for monochromatic component in the time series. And so when we combine these two, we can have a robust identification of waves that for this time interval, we have the 90 minutes that are already highlighted in visually in the first slide, but we noticed that there was also another one at 2.6 milliards. We can apply this also in the form of a dynamic spectrum, and this was on a random window of 90 minutes. And again, there is the same solar wind density, and here the power spectrum is limited in the reliable frequency range that is limited by the parameters of our technique. On the third row, there is the estimated background, and the bottom panel, there is the ratio of the two. And here, this black area represents the 2.6 milliards that we pinpoint during the second periodic density structure. The red dots represent the values in the frequency and time in which the gamma test is satisfied, while the green dots represent the monochromatic nature of the wave at this specific time. We can apply this technique also to observation of the GOES spacecraft. So we have this in the component, the field line component. And again, as we can see, we have the 2.6 milliards that is related to the solar wind, but also we can see that in the same range, there is a lot of other frequencies at discrete value. In particular, what I want you to notice is in this case, when we have this broad enhancement, if we look at only the enhancement in the power spectrum, we would only identify one frequency, but with the coupling with the F test, we were able to see that in reality, there are two frequencies here, one at 1.9 and one at 2.4. So this is also one of the advantages of using this technique. We also apply the same technique to an 181 ground observatory that we divided here in base of latitude, in high latitude, mid latitude, and low latitude station. On the left, there are the result of the gamma test, and on the right, the one with the F test. And the color scale represents the number of ground observatory that actually observe a specific frequency at a specific time. And these are the result along the north-south component. On the right, instead, these are the same technique instead applied on the east-west component. So in this case, we were able to identify a lot of discrete frequencies happening during this time interval, but in particular, notice that for the moment where we have the 2.6 milliards in the solar wind, we have this broad enhancement here that correspond to an almost 100% of ground station observed in that frequency. That means that the wave is very global, and whereas the other are more localized. In this video instead, that I'm going to show, so in the bottom panel, this is a qualitative map of the integrated power between 2.2 and 2.8 for the ground station that I used, and their location is identified by these gray dots. The white dots represent instead the station at which there is an enhancement in this frequency range, while the black dot represent when the wave is discrete. And this map is done for the north-south and east-west component for the time interval that is highlighted above in this green shaded area. That for context, I put the CMH index and the AE index. Here again, is notice how the CMH index is found a well correspondence with the red line that is the dynamic pressure of the solar wind. So as I go with the movie, you can see these PC5 waves that are more localized at higher latitude, and so some dusk dawn asymmetry. And when there is that wave in the solar wind, all the stations light up, and we have this global wave. And then again, we have here the onset of a substorm. We have intensification at higher latitude and some more localized wave. In this picture, instead, these are global map at a specific time. And in the table, there is a summary of the discrete frequency that I found in the solar wind, the GOES, and the ground. And each vertical column in the table corresponds to each row in this map. And in the board value in the table, I indicated the waves that have a more global character. And as you notice, they have some similarities with the fluctuation in the solar wind, the 2.6 that I already discussed, whereas in the first and the last case, these were broad enhancement that weren't monochromatic, but has an higher enhancement in power in the solar wind. And they found a more global character at ground. The other instead were mostly related at mostly located at high latitude, or some of them show a clearly dawn-dusk asymmetry. Here, what I want you to notice in particular is that in panel D, we have the 2.6 milliards wave that was already occurring in the magnetosphere, and this was related here, localized at high around the auroral over latitude. And then the same frequency became global when we have the contribute of direct contribute of the solar wind. We also did some polarization analysis for the same wave. This is just the north hemisphere. And the arrow represents the azimuthal wave angle with the color scale representing the left hand and right hand polarization. And in the table instead, the emphasized value are the one for which I found evidence of field line resonance, so phase reversal at the peak of amplitude, given station organizing at a fixed longitude. And here again, what I want to show is that in panel D again, this was a field line resonance that was already occurring in the magnetosphere, and you can see how there is the change of polarization. Whereas as we go to the global nature, we notice that there is the latitude, the resonance latitude at 73 and 77, around 73, 77 degrees maintained, but there is another phase reversal that appear at lower latitude during the global and directly driven, showing some kind of difference between the structure of the wave in between these two cases. For this event, we also have data from the Lanel satellites about of the electron fluxes between 50 and 6 MeV. And this was the time interval where the directly driven wave was observed. And as you can see, there were clear fluctuation in the electron flux in between 1 and 2.7 MeV. And this was observed almost globally. And we have a contribute mostly located at null from with the 3.1 that instead we think is more of a triggered wave generated inside the magnetosphere. And if we put that in residual flux, we can see how the direct, this is again in the top panel is the density, in correspondent of this peak, we can find evidence of drift resonance for electrons between 1 and 2.7 MeV. So to summarize, we have identified an interval of periodic density structure interacting with the magnetosphere. And we want to underline the fact that we have an overlap here between directly driven and global, and what we can call trigger in the more localized PC-Phi wave. And on this panel is in this video, there is the same global map as before, but for different frequency range. You can see the plethora of different ULF waves that happen during this interval, their location, and the distinctive difference with the directly driven wave. Thank you for your attention. If you have any question.
Thank you very much. That was really interesting. Tom, do we have any questions in the chat or Q&A?
We are all quiet. I think everyone's really tired at the end of the day. We've had such a long day of just constant ULF waves. Everyone is ULF waved out. But please do, if you do have a question, please do drop it in the chat at the Q&A. Otherwise, I will ask a quick one if that's okay. See, I've always been, I think ever since I read that first Kepko and Spence 2002 paper where showing basically that you could have periodic density structures in the solar wind and you could measure those same periods within the magnetosphere. I'm kind of always interested in this interplay between the two. So it sounds like if I've interpreted, please say if I haven't. If I've interpreted correctly, what you've got is you have a kind of mixture of these two things, and that you've got these periodic density structures in the solar wind which are driving things at that frequency. But then there's also other modes at different frequencies. Like you were pointing out there, you were saying here was a field line resonance observed at 2.8 millihertz before, but it's just been then enhanced after. So what do you think is, say for these events, the overall importance of both? So you've got, the periodic density structures in the solar wind versus then say waveguide modes or field line resonances that goes on to excite. What would be your importance on either?
Okay, so to your first question, yeah, this event was also to emphasize that we don't have only driven mode, we don't have only triggered mode. When we have this kind of event, we can see, since we are in the same frequency range, they can happen together and they can kind of mix. And in particular, for this wave, there was a field line resonance at high latitude. When there was the global mode, the amplitude of the fluctuation at ground station was amplified because there was both the effect of the field line resonance and the driven mode. So yes, they can mix and go like that. Regarding their effect on the magnetosphere, the distinction that I see is that the directly driven have this global character. It doesn't matter where you are. If there is a strong fluctuation, that is going to be observed everywhere. Whereas these other PC-Phi waves that I observed that I think are related to waveguide modes, some of them were observed after interplanetary magnetic field discontinuity. So there is also Foreshock phenomena. They have a more localized effect. So they can tend to not be so global. And I can show you here. I'll just quickly share. So you see, this is the directly driven. So you see all the stations are lit up. But if you go here in the top panel, this is a global wave that is triggered after the interplanetary shock. And you can see there are areas where the wave is not observed. In this case, for example, this missing area at 1.7 was missing because the wave were actually happening 3.6. So the structure is, I think it's different. And in that case is the plasma sphere or the dimension of the magnetosphere that playing a major role. So you have this, I think the major distinction is the actual global nature to a more magnetosphere dependent response.
Okay, great. Thanks very much.
If there's no more questions, maybe we should bring this fourth block to a close. I just want to thank all of the speakers. That was a really interesting range of talks covering all different aspects of why ULF waves are important. I'm going to hand over to Tom now to sort of close out the meeting.
Okay, thanks, Jasmine. Thanks so much for your help. Yeah, well, this is us coming towards the end of the meeting. Thank you so much to everyone for attending. And thank you very much to all of our speakers. Couldn't have done it without you. And also thank you to my co-organizers who also couldn't have done this without. So my plan for just now is we have the Zoom room open. I figure if basically, I was thinking we might take a 5-minute break just now so that our minds relax a little bit. If you want to hang around, then please just stick around for the next few minutes, go off, grab a cup of tea, come back. And if you're still here in 4 or 5 minutes, I'll promote you to the panel and we can just sit around and have a chat. That might fall completely flat, and after 5 minutes of that and us staring blankly at each other over Zoom, we decide to leave, and that's fine. There's no pressure, there's nothing organized at all. It's really if you just want to come on, say you want to ask someone a question, or you just want to see another friendly face who does ULF waves, just hang around for 5 minutes. If I still see your name in the list, I'll promote you to the panel, and then we'll be able to all have a bit of a discussion and see where that goes. So I'll come back in 5 minutes. But apart from that, if you are leaving us just now, thank you so much for attending, and I hope you have a great weekend. Cheers.